this is we're going to issue so many shares. So every corporation would have certain number of shares, and a portion of the shares you're going to offer to general public, and then it would get traded on Bombay's or Mumbai's trade exchange, and then you would assign a ticker symbol and so on. So that's a traditional IPO route. The cryptocurrency world, the route is very somewhat different, but there are a lot of parallels to it. So what you would do is that you would build out. So this contract that I'm pointing to you, the second link here, shows you how to actually create your own coins. So you mint you create like 1 million coins, just like how Satoshi, had 21 million of bitcoins. You would create a certain number of those. You would assign a symbol to it. Bitcoin symbol is BTC, and in this case, whatever that symbol is that you decide to have. And then you deploy this contract on Ethereum, say for example, because that's where you can put these Solidity contracts. Currently that's the only platform that allows to deploy this kind of contracts. And you publicize your address and you publicize your idea. And when the idea gets a lot of buzz, people look at it and say, "Yeah, this is a fantastic," the roti maker or what have you. And so you're not going to the venture capitalist. You're not depending on the venture capitalist to come and help you in the initial stage. When the idea is very radical, you can go directly to the public. And so this is the notion of an ICO. And this tells you the technology that you need to create your own coins and collect money from people, so that you can take that money, rent an office space in a big city, hire a bunch of programmers, bunch of marketing people. And so that's really how you bootstrap a company using an ICO, it's initial coin offering. And so this shows how to create those coins, and I will quickly show you that. And
that's copied. That's great.
I'm going to show, this is a YouTube video too. And then when you go down here, you see it's a build and deploy your own cryptocurrency. It's a short video, 21 video. And then when you scroll down, he in fact gives you the GitHub code for it. And it is a fairly short code. When you look at it, the code is not really very much. This is, and I'll just want to go through the raw. This is the entire code for that. And everything is in Solidity here. This is a fantastic way to create your own coins. This is how, for example, Helium has done. Helium has decided to go, so they are going to go into this IoT, like Internet of Things communication structure. Then they started offering HNT. Now they're a multi-billion-dollar company. Okay? So that's an interesting link that I've thrown in there, and I will share that. So this is actually, let me go back and grab that link and then put it on the chat window. I don't know what happens to those chat. I hope that gets recorded. I'll put it here. I will also send the slides like I have been doing. But I will not have a time to cover the second link. But I will go into details of the Solidity examples from the first link. Okay, let me get rid of that and go back here. I don't need this. So that's really the plan. Any questions on what we're going to be doing today? And so in the afternoon session, as per the schedule, I'm going to cover on how to build a gold exchange. It's a fairly abstract gold exchange, very, very simplified gold exchange, far from how a real gold exchange would operate. But what it gives you is the technical architecture, a grip on exactly what is needed from the technology point of view, what kind of a role consensus would play, and things like that. Any questions before I start showing some code?
No, Professor Ramki. I think we are good to go.
All right, excellent. So we don't need this anymore. I'm going to that and go here. And so what I wanted to show before I show solidity was what kind of an algorithm one would have to use to do. Remember that YouTube video when the guy was showing you the immutability of blockchains. If you make one change, how you would have to remine that block, and you have to remine the block that comes after that, and the other one after that, and so on and so forth. So the algorithm for this is relatively simple, but it pegs your CPU. It is a very CPU intensive operation. So I'm going to show you what is meant by mine. Remember, he had this blue button called mine, right? So this is what mine. So this is my name. I've written a small little Java program. It is self-contained. It doesn't really require anything else. I have hard coded. This would normally be a block that you're trying to mine, and I made this a final number, so that means you can't modify it. So this block, if you recall, it has the collection of transactions, it has a Merkle root, it has the hash value of the previous block, and so on and so forth. It has a hash value of the current block, and so on and so forth, right? And so, but then there is this blank spot called a nonce, number used only once, nonce field, that you are supposed to fill it in with whatever number is your choice, so that the number of leading zeros is either 17 or 18 or 19 or whatever that current difficulty level is. The more number of zeros in the prefix is required by the protocol, the harder you have to work in finding that random number. So so I set my integer. I'm just going to take this string. So this is read only. This is the block, and then I've just put in a fake string. Proof of work wastes a lot of energy, and so you cannot change that. But I've created something called string to be hash. String. This is a string to be hash, to which I add this nonce value. So the nonce is actually an integer here, but this has a type promotion in Java. So what this would do is that it would take the integer value, convert it into a string, and the compute the short digest on that. And the short digest happens to be an instance of short 256 in this particular case. And then once I get that, I cannot directly, unfortunately, I cannot directly use it on the way the Java library works, and then it returns as a byte array. And byte array is not really suitable to see if it has the prefix of zeros we have. So what we have to do is to take this byte array that is returned by the short digest, and I would convert it into hex values. And now once it is converted into hex values, I put it into this hash variable called hash, is of type string. And then I check to see if it starts with the prefix. Right, prefix is I hard coded it to 4 zeros, and then you can put any number of zeros you want there. And so if it starts, then I have found my nonce, and I'm going to print that value of the nonce, and I exit out of this for loop. The for loop starts out at 0. I'm just going to assume I'm going to go sequentially, and the nonce, and then less than. What does this mean? Some of you know what this means, stands for? I hope some of you know what this stands for.
Yes, sir.
What does this mean?
Can you tell the operator name once?
Shift operator.
Logical.
So what?
It
So
was a
what does-
bitwise operator performing left shift, performing 18 times. The one.
Yeah. So what would be the integer value of this? In a, like, you can give me like x raised to y. So if I shift it once, what do I get? 2 raised to 0 and 2 raised to 1 and 2 raised to 2 and so on, right? If I start with 1, and I shifted once actually. So one is without if I shift 0 times, I'm already at 2.
One is multiplied with 2 power 18, sir.
Yeah, exactly. So if this goes up to 2 raised to 18. So this is more efficient way of doing this than to, for example, you can also do this, right? You can say math.pow, right? And then you can put 2 and then 2.0 and actually I believe you can just do 2 and it will promote it to a real number. You can do that too. This is more time consuming than just to take, especially if the base is 2, you can just simply shift it like that, right? So that's what I'm doing. So now you can shift up to 32 numbers because it's an integer. And then unless it's, then you will overflow, you'll overwrite the sign bit and so on. But in any case, we're not going up to 32. And so this, all I'm doing is I'm just keep looping and then coming up with one number after another number, add it to the string to be hashed, right? So proof of work with energy, that cannot be changed. But this is the variable part that I changed. This is the nonce. And I check to hash that, and I get the byte array, and then take the byte array, convert it into from bytes to hex value, take the hex value, put it into the string variable hash, and take the hash value, and then check to see if it has a certain number of zeros in the front. If it does, I'm going to break out of the loop. And because this function requires me to put this inside a try-catch loop, so I have an exception handling routine for the digest. Any questions on this code? Fairly simple, right? And this is all really there is to do mining. And so if I were to run this, let's run this. And you can see this at the bottom. And this yeah, there you go. You can see the nonce value here, right? And it found the nonce, and the nonce value is equal to 225.46. If you go back to the slides I distributed yesterday, and there is a link to online tools that where you put in on the top window a string to be hashed, and then if you take this string, proof of work with a lot of energy, maybe I can just simply show that online SHA-256 online. So if I put in, for example, proof of works waste a lot of energy, and then I get that, except now it doesn't start with zeros, right? However, once I append this integer, hopefully you'll get 4 zeros. You see that 4 zeros there? Does everybody see that?
Yes,
So,
sir.
yeah. So that's the idea of mining. It's really as simple as that. And if I make one change here, and then if I put an exclamation mark, this, and then if I run it again, it will be a different nonce. Right? Oh no, actually, that's surprising. Actually, this is the same nonce value. So something happened here. I wonder what went wrong. And let's see. Huh. I don't know. There's something is broken here. It's giving me the same nonce value, and it shouldn't. Oh, maybe this is maybe the way it is computing the digest is this is not getting refreshed for whatever reason. Yeah, I don't know why this is not changing. It should change actually. So as you can see that the moment I put an exclamation mark, you get a completely different. So anyway, that's the idea of mining, and so I wanted to quickly show you what mining looks like. And there is the function that the helper function that I've not gone into. This is an entire file. And so this function from bytes to hex is here. that I have not shown. It's just a helper function. There's nothing interesting about that. The entire algorithm for mining is right here. Okay. So I'm going to stop here and switch gears and go to start looking at Solidity. Are there any questions on mining? How mining is done?
No, sir.
All good?
Yes, Professor Ramki, all good.
All right. Okay, so the first thing that you guys are going to do is that this is that website link that I have given, and this is what we'll try to get through today in a relatively easy pace that you're all able to follow what is going on. And the first thing you're going to do is that you go to remix.ethereum, and it tries to autocomplete this to com, and it goes to the wrong site, and you want to be at org. Remix. So this is remix.ethereum.org. And then you get an IDE. This is like a remix IDE. And this is the entire integrated development environment for Solidity inside your browser window. And so you might wonder, what happens, I've opened it here already. So I have been working on some of these files to show you guys. Actually, go back to this, and I will explain to you what different panes are here. You might wonder, what happens to this? What are the different buttons here? This is clearly the home button. I'm just going to do a quick run through of this tool. This is the home button, and it shows you how to publish this to GitHub and whatever code you develop. And it has different plugins. It has Solidity, which is what we're interested in. A few other things that I don't even know what they are. And we are going to use whatever we develop here within a virtual. We are not going to use Ethereum virtual machine. Instead, we're going to use a JavaScript virtual machine that is part of this this embedded IDE. And then some of these other options you see here. For example, there is injected Web3. Is that if you want what the development you're doing in here, if you want that to interact with a wallet such as this, like this is called a MetaMask wallet, and then that automatically gets triggered when you do transfers of Ether. It shows that the digital wallet also shows that. And then you would need to use this Web3 provider. I don't know how many of you have already heard what is Web3. Web3 is the decentralized internet. Currently, there is Web 1 and Web 2. Web 1 is the very old client server computing with web servers and database servers. Web 2 consisted of all the social media like Facebook and search engines and Twitter and what have you. And what people now refer to all the new technologies that have crypto in them, decentralized finance, and distributed apps. They call them DApps. There is DAOs, like decentralized autonomous organizations. All this collectively is referred to as Web3. So if you want like an injected Web3, so where you're not only testing self-contained programs, but you also want them to interact with the digital wallets. This is called the little thing that you see here. Let me do something. I'll make it bigger. That wallet is called a MetaMask wallet, and you can choose that there. But for now, all the examples we're going to look at are going to be self-contained Solidity scripts, like smart code. So we're going to leave it there like that. And this IDE comes with a certain number of fake currency. And so these are all different accounts. It gives you a certain number of accounts, like I don't know how many there are, like 10, 20 accounts. Each one has a fake 100 Ethereum Ether currencies there. All right, so that's what the accounts here are. and there is a few other fields. So this is I was curious as to what this was. This is fraction of ether. So 1 ether is equal to, I showed you on my PowerPoint, it is 10 raised to 18 ways is equal to 1 ether. Okay. And so that's you would when you're doing transactions, you can put certain values and say, I want it to be 10 ether, and then you choose that 10 ether, and then you can send that from one address to another address, and things like that. All right. So the next thing we have is the file explorer, and the file explorer is where all your scripts are going to reside. And when if you want to create a that's for creating a new workspace. Within the workspace is what all these things you have. If you want to create a new contract, you click this unfortunately this there you go. Maybe now you can see better. Yeah, there you go. So I've gone through that crash course, and I've taken some of the interesting contracts, and I've actually ran them. I ran them on a different version of the compiler that the guy was using, and so I fixed some of the issues that come up because of that. And so this is the compile pane. So when you choose this one on the left, so this is actually this collapses this vertical bar, right? And so this you can choose which version of the compiler you want to run, and so you can pick some of the latest one being version 0.8.7. You can pick something like this, for example, and when you have scripts that are ready to be deployed, they get deployed on the network, Ethereum network, at a given address, and I will show you how the deployment itself happens. And then once they're deployed, and people will be able to call you can invoke those smart contracts that will change the state of Ethereum ledger. So the way the Ethereum doesn't have the notion of the blockchain the way Bitcoin has. Instead, it has smart contracts, it has accounts, and it goes through state changes as a smart code is executed. Okay, and there is a few other buttons that we don't really need to be concerned with. Right. So that's what you have on the left-hand side, and so your code development begins by choosing the file explorer, and then saying that I went through this, and then I said, okay, I want to create my own first Solidity script, and I created one like that. And so even this you don't really need to struggle too much about well, how do I put this together. This itself comes with some sample code. Okay, so I'm going to go ahead and create what I've created. Instead, I will look at the three sample things that it came with. This one underscore storage dot solidity happens to be the simplest one, and the other one is a little bit more complexity to this, like this. And there is a third example one that has a few more functions. So instead of so you can actually take this and modify it, which is what I've done. And so let's actually take a look at what they have given us, and how I modified it. It's a fail. So just you must start with this is the thing with Solidity, is that you must define what is called an spdx license identifier. Okay, and if you Google this, so let's copy this and see, Google what is spdx, because even I wasn't aware of it. And so so spdx stands from a Linux Foundation, some open source foundation. It stands for the Software Package Data Exchange. So because that code is going to be there out in the open, it needs to have a certain like tags as to now, can somebody copy it and reuse it? Can it only be executed? And so I'm guessing this has something to do with that kind of tag as to how it should be used. So spdx license identifier, and so this is a GNU public license 3.0 is how it is identified. I've simply just copied this line. If you don't have this line, it will not compile. So this is a requirement, though it looks like a comment. This is a requirement. Okay, so now I'm going to suppress this file explorer and only focus on the editor. And the second line here, this is what came shipped with this remix IDE. I'll get rid of that. And this is a tip how you comment out things, and you say the title, and I'm guessing that this is also has an auto documentation facility by doing that. The title of this is it's storage and store, and the comment about that contract is that to store and retrieve value in a variable. All right, and this very, very simple contract. So this is everything that is there to this contract. The name is storage. It has one simple one variable, and u into 56 is a unsigned integer. So this can get as big as 256 bits. So it can get as big as 2 raised to 256, and it's unsigned. And the variable name is a number. And then here you come down here, and then you have a way to put some value into that variable. So store and retrieve. If you are used to object-oriented programming, and if this is a private variable, it's not visible to the world outside. This is what is called a setter, and this is what is called a getter. Right? It's really, really simple function. Okay. Right. So now I need to get back here. So I've done something similar. So when the moment you go to strings, it becomes a little more tricky, and then you have to talk about where the memory is going to come from for that to store the value of the string. And so the syntax is a little different. And in addition, I've decided, okay, I'm going to create this variable called string, and I've just thrown in a variable that I don't even use. I don't use it anywhere, called a Boolean variable. And I set that to a true value, to constant true value. And when this is deployed, the constructor automatically gets called, and it doesn't require, fortunately, it doesn't require any parameters. But what it does is that within this public variable str, it stores the value default initial value, the string. And when you try to get it, if you have not set it to something different, it will return that. Otherwise, if you have changed it meanwhile using this set function at the bottom, it will return the new whatever the latest value is. And this is a function that is public, and this is a function that is it's a view function. It's a read-only function, so nothing gets changed, and it returns a string. And then this is again one of those requirements for this variable called, you have to put that in. This is a solidity specific feature of dealing with strings. So okay, so if I have this, what do I do? So if I create this, first thing I do is that, okay, there's one other thing I need to show you. At the bottom of this screen, there is this little bottom arrow. I just disappeared completely. Hold on. What happened? So I'm going to have to refresh this, reload. And so I go to, so this is the pane that I did not tell you what this is. This is where your errors and successes and all these things appear here at the bottom. You can collapse it, you can maximize it, and again you can do the same thing as to show you what it is trying to tell you here. And you can clear the screen with this button here. It clears that, and so on and so forth, right? So now let me get back to my scripts, my contracts actually. So I created my first Solidity program. So let me take that, and I don't. Yeah, let me keep that around actually. And this is what I just showed you. Okay. Okay. What I would do is that I would go to the compile button, and then there is one thing that I glossed over that I would like to tell you further a little bit more, is that this statement right after that you identify the license, you have to say which compiler should be used to compile this smart code. And you're saying that it needs to be, actually I have changed it from the original script. I've changed it to that it needs to be at least 0.7 and but not greater than or equal to 8.11. It needs to be strictly less than that. And so if you look at the compiler that I have chosen here, it is 0.7.5 and it falls within this range. And we are good to go here. And so if I hit the compile button and you see the green tick mark here on the left, that says that it's all good. And so now that it passed the compilation step, and next thing I'm going to do is to deploy it. And then I go to the next button down, and I'm going to use the JavaScript virtual machine for the environment. I don't need to set any of these things. And and then at the bottom, you can see that it is saying currently you have no contract instances to interact with. So this is all just development. I'm not even deploying anything on Ethereum network, but this is very close to how you would do it in a typical deployment of smart contract onto the real address. So you don't even need to set any address. So you hit the simply deploy button. So what you see here is that this is a good thing, that when you see something green here, that means that something happened correctly. And so let me suppress that and take a look at what it's trying to tell me. And so if I open that out, it tells me that it got deployed. And then it gives you some addresses, the string storage constructor. Because it's a string, it needs to have some storage associated with it, and it tells you which account it came from. Actually, yeah, it tells you which account it came from, and then the string storage constructor got called, and so on and so forth. The hash values, different things here. So that's what happened when I hit deploy button. Okay. And let me go back and take a look at how I can interact with this. And so where is this deployed smart code contract? It is down here at the very bottom of this screen. See. This is called a string storage. All my case, uppercase, lowercase, all went to hell, and it just shows me like all uppercase. That's what it looks like. So it has, these are all the things that are exposed. Okay, you can set a value into that string variable, new str value, or you can get it. And I have this my boolean, which I'm not neither setting nor getting, right? So if I now simply just ask without doing anything, get me the value, so that it tells me that it succeeded. This whole thing succeeded here, and I don't really want to look at this. Call it came from here, and this succeeded. I'm going to suppress that instead. What happened here? Reload. Okay. And so where were we? So we were here, the deploy chain, and currently you have no contracts. So go to deploy. Solidity compiler. Since we reloaded it, it lost the context. And then the one I was working on was my first program. And I go back, compile, and I after compilation, go back to here, deploy, okay, and open this thing at the bottom. And then if I simply say now get me without setting any values, it should give me the default value. And as you can see, it has given you the default initial value. Okay, but if I want to set something else, set it to today is Thursday, and type in any string you want. You set it, and then you come back and you get it, and it will change it the value to today's Thursday. So these are the functions that are exposed. This is how you would do setting it. So that's str variable is also a public variable, so you can directly see when you click on that, it shows you the contents of that variable. So this is like the very first program, like the hello world of Solidity. Any questions on this?
Sir, where we deployed this contract, sir?
So in real life, you would be putting it on Ethereum network. So this is simulating a similar kind of a network. It is a fake network, and it is creating fake currencies like what we had here. So all these currencies are all fake, but this language and the compiler, these are real Solidity. So in other words, if you take this and if you want to deploy it on this has absolutely no use, but if you want to deploy this similar to this kind of a smart contract on Ethereum, there are steps that you can go through to put it on a real one, and that will cost some ether. That will cost some money to put it there. So right now it is just running in this simulated Ethereum network that is part of this Remix IDE. I hope that makes sense. So this is creating
Okay,
this is creating fake addresses. So you see the string storage is stored at this address. This is like a hex value you see here. It is just some fake address it just creates in the memory, and that's where it is getting deployed. All right.
IPO is smart contract, sir. Prefer
What is
with IPO. Initial public.
yeah, so that I couldn't get the question clearly. Can you repeat the question, please?
Yeah, sure, sir. Like we discuss, I could not get what exactly is smart contract. Like I am asking about example. Is IPO a smart contract?
No. Smart contracts is a way how you do transactions on the Ethereum cryptocurrency. So in blockchain, you would submit a transaction through your wallet. You take a Bitcoin compliant wallet, and then you say, I want to. Remember yesterday I was showing you have some inputs that you control. So say you have like 3 public key, private key pairs, and you have 10 Bitcoins in one, 5 in the other, and 20 in this other one. But then you combine all of them, and then you create a transaction and say that I want to send from those addresses to some other address, and you take the change back. So that's how the transaction in Bitcoin works. Here it is done in Ethereum. It is done using smart contracts. So the transaction has to be part of this smart contract. So this is how the things of value change hands. I hope that makes sense.
Okay, sir.
Yeah. No, you have to ask me. No, don't just say okay. Just you have to tell me how I can make it any clearer. Please ask more questions. Right now, so what is it that's confusing? So all cryptocurrencies are about creating currencies and that potentially have value. In fact, one ether, if I Google the value of ether, it is in thousands of dollars. Ether price, this you can see, is 3,000, over $3,000 of value, right? So the market capitalization of Ethereum currency is $379 billion. So that is how much that currency is worth. So people buy this Ethereum using traditional dollars, or whatever euros or whatever currency you have, and then they transact. They buy and sell, give it to other people, or convert this into helium network and things like that. So there is a network just like the Bitcoin network, except the way you do these transactions is different. In Bitcoin, transaction happens on the Bitcoin blockchain, and in here this so that has a ledger of sorts that keeps track of all transactions. Remember I told you it has all transactions, and there are 700,000 blocks, and each block at approximately 1 megabyte. The entire Bitcoin blockchain is around 400 gigabytes, and so the miners would have to check and see each transaction by tracing it back. That is the legitimate transaction. So but this is a little different here. Ethereum, see, this is what actually I started out today. Remember, if you recall, there are certain aspects to today's lecture that you won't completely understand because we've never really covered Ethereum cryptocurrency. And Ethereum is quite different. It keeps track of what is called the state of a ledger. It has state is like a set of variables and what their contents of the variables is. And the way it maintains its currency, the way it does its proof of consensus, these are different for Ethereum. And we've never really had a chance to cover that. But all excitement within the cryptocurrency, all applications, new applications in decentralized finance, and the ones I've mentioned, they are happening on Ethereum. So that's the reason why I thought a good way to get you introduced to something practical. And if you are so keen on building any distributed decentralized finance applications, you would have some introduction to a language using which you can build these applications. So where it is deployed, they would be deployed on Ethereum network. Since I've never really introduced to you what is an Ethereum network looks like, the state of the machine, and so the places to look for them is if you just look for EVM, which is a Ethereum virtual machine architecture, and that will tell you what happens to smart contracts, where smart contracts are stored, and so how smart code is executed, and so on and so forth. When we've never really had a chance to look at that technical architecture of Ethereum virtual machine. So that is the reason why, and that I know that this you're wondering, okay, where does it completely fit? I get that, but beyond, I really cannot help that because within the time constraints we have, this is the best use of our time. I hope that that satisfies your question.
Sure, sir.
So when you hit the deploy button, and so there would be different kind of mechanisms for a real network. It would get deployed on Ethereum network, and then you can do transactions on that. So if maybe when you see some more examples that I have, you will have a little better understanding of how transactions are performed, how coins are exchanged, and how different parties can engage in selling coins and in return get some money in return and things like that. I have some examples, but I don't know whether we'll be able to get through them. So let me get back to my file explorer. That's the first example. And my second example is equally simple. This program is, let me just get rid of the side pane. And let me get rid of that. Okay, and then I can do ++. This again is I copied from the previous file, and without these two lines, it is not going to compile. So when you try to experiment Solidity without those two lines, it will not compile. And this is a name again. Contract starts here and ends here, and so again it has the same name. The only thing that is different here is that it is telling you how to use an enumerated type. The enumerated type here happens to be state, and there are three possible values for the state: waiting, ready, and active. In the constructor gets called automatically when you deploy the contract. So that is equivalent to executing it. And the constructor, when it automatically gets called, this variable called state, which is of the enum type, and it's public, and it is set to the waiting. So initially it is set to waiting, and you have a function called activate, which is exposed to public. Anybody can invoke this, and they can change the state from whatever it is to active. And then you can query and say, look at and say what kind of state this variable is in, state is in. Then you can return if it is. So all you want to know is if it is active or not active. So if it is ready or waiting, this will return false. The only time it is going to return true is when it is active. So that's also fairly simple program. Let me get my compiler pane, and so I'm going to compile it again. Again, I get a green button, which is good. And then I go to my deploy button and I hit deploy. And then where does it get deployed? It's going to be at the bottom. Okay. And first before you deploy it, what I like you to do while you're playing around with this IDE is to clean out the previous deployments. Okay, because otherwise this whole space is going to be confusing as to, there are several different contracts, including the old ones, and you don't know where the one you just deployed, where is it, and you have to search for it and so on. So before you even hit this deploy button, the brown button here, just clean it out and then deploy it. So now I'm looking at my second .sol. Contracts at my second .sol. I'm going to go, since it compiled cleanly, I'm going to go ahead and hit the deploy button, and there you go. And this down here at the very bottom, it's hard. I don't know if you can see it at all. It's in light gray, and then when I pull it down, this is the address at which it is residing. This contract is residing. And I can take that address of that smart contract if I so choose. I don't need it, but if I just copy it and I can put it here, for example, just like, okay, that's the address. That's how it looks like. So I can activate it. I can query if it is active. So what do you think I will get if I hit this button? What does this function return? Well, take a look at the header for this. It returns a Boolean value, right? And what is it checking? If it is checking if the state is active. So is the state initially active?
Yes.
No, it is not. Actually, look. The constructor is set to
Waiting. Okay.
Yeah.
Okay.
If I put here active, then it will return true. So I see it returns false. Right? So the state is okay. So here I'll activate it. Now if I hit this, this changed to true. Right. And so this is to hit this. I'm sure you're all familiar with C++ and Java enum types. This is assigned an integer value of 0. These are like ordinal types, what they're called ordinals, because you can compare any two. This is assigned a value of 0, this is assigned a value of 1, and this is assigned a value of 2. So if you go to this variable directly and say, tell me what the current value is, that shows a value of 2. It's a 0 indexed array of 3 values, so 0, 1, 2, 3. Since you made it true, you just click the is active button, the value it shows to be 2. All right. Any questions on this program?
No, sir.
So it's pretty good.
Yes, sir.
Okay, so let me do one thing. We have a couple of minutes before you have like a 15-minute break now, right? Yes.
Yes,
Karthik?
sir.
Yes, yes,
Okay.
Professor Ramki. We have just 2 more minutes. After that, we'll take a 15 minutes break.
Yeah. So let me show you what I'm going to cover. So this is another. In fact, they're all TOEIC programs, because because this is like a crash course within like a couple of hours how to come up to speed with some of the most of the features of Solidity. Okay. So the one I'm going to show you is what is called the time control. I can get rid of all these tabs. I don't need them. And the time control is that you're going to say that this how you can use the clock value to perform a certain function. Okay, so this is what is unique about this smart code. So you can perhaps say that you know how contracts are written, right? And you say that this contract is, well, like a check is a good example. When you write a check, you say that that check is, you put the date on it for a reason. Because if the check is very stale, if this check is like more than 6 months old, the bank is not going to honor that. Something similar here. So if we can look at the value and say that the timestamp on that is too old or too new, you're not going to perform a certain function. And I'm going to show you how to do that when you come back from your break. Okay, have a nice break and I'll see you in 15 minutes.
Sure, Prof. Ramki. welcome back after the break. Over to you, Professor Ramki.
Wonderful. Okay. So, like I told you before you left, actually, maybe I should not tackle time control. I am going to do something simpler first. Let's go with arrays. Yeah, let's go with arrays. I think this is probably a lot easier. So this has two additional data types. One's a struct. This struct is made up of two strings, underscore first name and underscore last name. And we're going to create an array of such structs that are made up of person array. So this type, and then you create an array out of that. And this is made available to the public. And this variable, we're going to call this people. There is no, so just like before, you specify the license, you specify the compiler version, and this has arrays. But to my dismay, I found that there is no way to actually find the length of an array. There is no built-in attribute for it, so you would have to keep track of it, which is kind of annoying. But it is what it is in Solidity. Oh, why I can get rid of these things? Okay. In any case, let me just make it a little bit smaller. I hope you can still see, and I don't need this explorer, so I will toggle and go there. Yes. And so the function here is we have exposed one person that's of type public, so we can add a person. This is of type string. Again, I told you this is the artifact of the fact that it is Solidity. Solidity contracts reside on the network, and for string variables, you have to put in this modifier called memory. In the first name, you provide first name, and you provide the last name, and then it would take those two values, create a struct of this kind, and push it onto the array. So this is how you add elements to this array, and then you keep track of the count, how many people there are, which is an unsigned integer of 256 bits, and then you increment that by 1. So here the assumption again is that it is initialized to 0, though there is no explicit initialization here. So this is all looks good. We can go down here to compile it, and so here first, let's go ahead and compile it first. So we don't need that yet. Now I go down to my deploy button, and then it's offering me to deploy arrays.sol. And this is my account that starts with 5B3 that has a certain number of ether. Right. And so currently there is this old junk from before. So the first thing I'm going to do is clean it up, and then I'm going to hit this trash can button that cleans out. So then it tells me that currently you have no contract instances to interact with, which is how I want it. And then now that I cleaned up my, I'm starting with a blank slate. I'm going to go ahead and deploy. Once I deployed it, it's at the very bottom, and my contract has been deployed at this address. So one of the things that your partial answer to some of the confusion you might have, where is this deployed? And I said, an Ethereum network. Where is the Ethereum network? Ethereum network, just like how blockchain networks runs on computing facilities provided by the miners. Miners are the one they are offering their hardware, software, and that forms a network. And similarly, Ethereum runs on people's networks, and people would have to take a stake in this, put the money into this, and there is this notion of what is called IPFS. And if you Google that, you will see this is a storage facility that's in the public domain. It doesn't belong, it belongs to people, but then people have given access to some of their storage facility. And the smart contracts can be deployed there, and you can get a unique address on that IPFS file system. And this potentially could be one such address. And so that's where these things actually physically reside. So all right, so if I right now there is this array is empty, there is nobody in there, and then we can put in the first thing. We can say that this is part of the GIAN course, and like that, and then I say add person. And then now, how do I see that? If you just simply hit people, it's not going to show anything. But if you hit people count, it got incremented, which tells you that it got added. And in order to find out what this array contains, if you hit this thing, it is not going to show the entire array. Now, this is unlike in, for example, in Python. Python has a nice way to visualize what an array contains. And here it doesn't. And then here you would have to give the index and say, tell me what is in there. Then it will come out and tell you this is there is the index is 0. The underscore first name contains GIAN. The last name contains course. That's how the arrays are used in Solidity. Let's go take a look at what other data types we have. Yeah, perhaps we can look at access control next. And access control also has a way to associative arrays. So that's a good way to get introduced to that also. So let me minimize this. And it has a few other things that, and I have tried to comment out what are the new things you are learning in this program. What we have here is hash maps, what Java calls hash maps, which are key value pairs, right, or associative memories. In this particular program, I'm going to show you. It also has this particular type that is unique to Solidity called address, and that's a 20-byte value. And there's two variations of address, another one called address payable, and address payable has two attributes, two functions that are associated with it, one to transfer and one to send. And similar to assertions in Java, this Solidity has a require, and we are going to use require in this function. And then there is another one called message.sender to see who the caller is. And if the caller sent in any money, we can take a look at how much money was sent by looking at msg.value. So if you have ever coded in web programming languages, for example, if you want to see the get values, the parameters sent by get method, the parameters sent by post method, there is a way that the HTTP protocol allows you to examine that. It is very similar to that. So whoever called this contract, you can figure out who that person is and what value came in the form of an amount. And then the modifier internal says that that visibility for that function or the variable is only local. It's like a private. It's equivalent to private in Java. And then you're going to see this some combination of strange characters like this, and I'll explain to you what that is. So this is building on the same thing, except this is laid it out for readability reasons. This is the function name, the two parameters it expects when you call this function. It is saying that this is exposed. And what it is saying here is that the only owner can add a person to this array. Okay, so public, and then it adds this restriction that only owner can modify this function. So if someone else tries to modify it, it's going to fail. And so this increments the count of people, and increment count is down here. It's very simple, and it keeps track of the array length. Remember, I told you that there's no way to get the length of the array. You have to maintain it yourself, and this is made internal. So that means people have no reason to find out what that increment function is, because if you expose this to public, then they can play havoc with this number, right? So this is a private function. This is visibility is restricted to this inside this contract. And as soon as you deploy it, this gets called. And the person deploying is presumably the owner. And so this is a data type that is again unique in Solidity. So the deployer has an address, and I've been showing you that address. It looks like a hex value, and we call that address as the owner. And then we're going to retrieve who that owner is by looking at the message. So this the meta value that comes from deploying it, and then you retrieve who the sender is. You store it in the owner value. Well, how is this owner value used? The owner value is used to make sure that, remember here we put down as only owner can change this. And so the only owner is a function. It's actually a modifier. So this is a special kind of a function. What this does is that it asserts that the message.sender is equal to the owner. So the one who deployed it is the one that is trying to add a person. Okay. If this assertion fails, this is going to abort. Otherwise, this is going to continue executing the function. So this strange operator that looks like the underscore and the semicolon, typically people put it either before or after. So if I were to take this and put it above, so what that says is that, okay, go ahead and execute the function. So if I had this instead, go ahead and execute the function. On the way out, check the assertion is true after execution. Right? This could be, I will show you what are called events, and even event could be sending out a message saying that everything worked well, or it will report something else. Okay, so but right now this make sure that the person who is attempting to change the person array is the owner, and only after verifying that is the case, it goes ahead and execute the rest of the function. This increments the count and puts it into the people count is equal to creates this object and puts that into that array. Any questions on this, on the code? No questions? Okay, there are no questions.
No questions, Professor Ramki.
Okay, all right. If there are no questions, then we can go ahead and compile it and deploy it. So I'm going to hit the compile button and compile access control. So this is basically access control. So this is log how you in Unix you say that only I should have the execute permission. No one else should. I'm the owner, and I should only have the execute permission. To some degree, you have accomplished something like that. So this answers the question. So the previous there was question, is that Manasa who asked the question? Where does it get deployed?
Yes, sir.
Yeah. So this is, you see this IPFS I was telling you, and if you do research on what is IPFS, this is where the Solidity contracts reside. This is the layer, storage layer for Ethereum contracts. Okay, so and right now we are not doing that. We're just deploying it in this fake network. Okay, so compilation succeeded or not? Let's go ahead and compile it. And it succeeded. I got the check mark here on the top left. Then I need to go into my deploy button and clean up the garbage first, all this nonsense. And so I'll delete everything. And so then it here it confirms that I have nothing to interact with. I'll open this and keep it open to see that when I deploy it and when I'm interacting, that I'm not getting any errors. So even this pane is like the standard output for us typically, and I'm going to clean it out so it's all blank. Now that we've compiled it, let us go ahead and deploy it. And this green button means that it's successfully deployed. And we can open it and see. It will give you the address where the smart contract resides, and so on and so forth. And then what is the constructor for this? So the constructor doesn't require any parameters. But then it did capture in the owner field who the owner is. So if I go down here, then those are the ones that are exposed to me because the owner is a private variable. Unless you put like public modifier, everything else by default is private. So that's why I don't see it here. So wherever you have public, like the people count and people and add person, they're all public. So if I hit this, it's going to show me that the count is 0 initially. There's nobody in the array. Not surprisingly. Now if I go ahead and put this is what we have been using as the first string. Yours and add person. Again, this is good. Green, you see green, and that means that the transaction executed correctly. But now if I come down here and change the account where this is getting executed to some other account, this shouldn't work, right? Because again, this is going to capture that address where this is coming from, the request is coming from. Compare it with the owners and say that, well, you're not the owner, you have no right to change the array. So we can use the same values, or we can just say this, I'll close this, should not get added. And close that, and I hope it doesn't get added. Unlike that mining example I was puzzled by that byte array never got refreshed. So now if I hit add person, you see that red thing? So that means it didn't go through. And so there was an error. And if you do the people count, it is still 1. Okay, so this is how you enforce access control. And if I go back and change the account back to that account, those are all my accounts actually, because I am the one running all 20 of those accounts. But the account I use to deploy, if I use that to add the person, there shouldn't be an issue. So that did succeed. And the people count is 2 in this case. And if I want to look at the second element in the array, I would put in what? Index 1, right? Because it's 0 indexed, so it will tell you, what the hell happened? Okay, oh, maybe it retained something from before. There you go. This should not be added. So it looks like we added that GIAN course a couple of times before. Anyway, so this gets added as long as the account owner is the same person who deployed the smart contract. So that's how you would do access control. And the way you get those, the original address that deployed it is by saying message.sender is that captures the address of the account that deployed it. So we deployed it using that 5B3 account. Okay, and then you check to see that the person who is calling this function, add person function, only owner, and then that only owner is a modifier for the function call, and that requires make sure that whoever is calling the function is owner. If this evaluates to false, the assertion fails, and the smart code execution is aborted. All good?
Yes, sir.
Okay, so what do I want to do next? So let me go back to my file explorer. I've done access control with the ownership. Now let's look at time control. So remember, these are all contracts. It's difficult to explain to young people what a contract is. Actually, many times you enter a contract without knowing that you're really entering into a contract. Some examples are like if you are renting a house. I don't know if at least my experience is that people don't enter into a lease, which is a legal instrument. So lease has clauses like what the rent can be, and you get them to sign. Actually, that is happening in bigger cities, but in smaller places, maybe that may not be happening. So lease is like a legal contract. So the idea of Ethereum and smart code is to have contracts that are completely electronic. Okay. So the time control, for example, say that you are going to tell the tenant, say if you own a house and you are renting your apartment to somebody else for a couple of months, you are going to put a time control and saying that here is a contract and this resides on Ethereum. And so just imagine a world where the key to the apartment is digital. Okay, so that digital key is not going to be revealed to the tenant until a certain moving date happens. That's a natural example, right? So today, for example, is what is it, February something, right? February is 9th for me and 10th for you, and you get into an agreement with somebody saying that I'm going to rent my apartment for the months of March and April, and you execute this smart code contract to release to a digital punch code key, right? And imagine your apartment has this lock where you punch in a code and it opens the door instead of like a physical key. That's entirely possible, right? And the way you can set up this solidity contract is that on the 28th of February midnight, it emails that person the code for your door. Okay, so this is how you set the time controls and execute these contracts. So you try to get legal contracts moved over into the digital realm. That is the dream of these crypto enthusiasts. So all the legal contracts will move away from paper, pen to digital. So, and one could potentially use these things to accomplish that. Okay, so when I look at a file like this, it's a fairly simple file. Actually, these are all, like I said, these are all toy programs. And I'm going to suppress this pane. Is that the first thing I look at is that, okay, where does it start? Where does it end? So again, we have to ignore these things, right? Unfortunately, there is no way to fold them. So I can fold that, but I cannot fold this. But anyway, so I look at where does it start, where does it end? So that tells me this is the contract. And the first thing I look at is how is it getting initialized? Okay, and this is a constructor. Again, it doesn't take any parameters, but it sets this variable called start time, and we can go look at what this is, what start time is, and sets it to certain value. And we'll figure out what that value in a second. And when you come and take a look at what that variable is, it's called the start time, and it's an unsigned integer of 256 bits. And what did we say this was? Anybody? What does this mean? I introduced you in the previous program, I believe. No answers? No answers, Professor Karthik there? Nobody is giving answers on the chat box?
No answers are flowing through, Professor. Participants feel free to let us know.
Unmute. Yeah, or
Yeah,
on
unmute
mute
and
and
let us
say,
know.
so clearly, just based on syntax highlighting, you can tell that it's a type, right? And it's a type of that, and it is giving two tuples inside, and it is what looks like an arrow. It's going from the left side to right side. What does it remind you of?
Changing.
Like a dictionary.
It's a dictionary, yes, or it is. We know actually that is not the dictionary is not the right term that is used. The term is the associative memory or hash map. Java calls them hash maps, associative memory, or key value pairs. Okay, so in a typical array, array starts in a zero. Index-based arrays, you can only index them with integers, positive integers most of the time. Though some languages allow you to index them with negative numbers. That's not always convenient, right? And a hash map could have, given a string like my name. I want to find out my height or something like that, right? And so then those are key value pairs. That's what this is. This is an associative memory. That's why it's called a map. So key is mapped to a value, and the key comes in the form of an integer, unsigned integer. It's a small integer, and it is mapped to a person. And person, we said, is a structure, and it has an ID. Person has an ID, and it has a first name. Person has a first name, and person has a last name. So this is an associative array, and it is visible to everybody. And this is since this is a collection of persons, and this variable is called people, like a plural of person, right? So that's what this the type declaration people is. All right. And we will look at what this is what is significant about this program. And remember what is this modifier? We just saw it in the previous thing. Remember, it said that it had this assertion, right? And that assertion made sure that the person who is calling the function, so in this case, the modifier applies to this add person. You can only add person, or the example I was motivating with, you can only release the door code only after February 28th midnight. Okay, so that's really how this assertion is applied here. Before it was ownership, and now it is based on time. Okay, well, how do you actually find out time? And so probably some of you who have coded a little bit know that there is this Unix clock that keeps track of number of seconds that have elapsed since 1970 or some such year. And you can get that number. So that you have to hard code that number and so you can and put that into start time. And what this makes sure is that when somebody comes to add a person, and then it looks at this block instead of message. This time it looks at block, and it looks at the timestamp, and it ensures that it is at least the start time. This you can encode February 28th, 2022 as an integer. So how would you do that? The way you do that is that, let me show you by going to a tab, and this is what it's called epoch time converter. Okay, epoch time. This is a Unix timestamp, and this you can see that this every second this integer keeps going up, right? So this 164447545. So what I could do, and I am going to say, this is the current time, right? That's not good. So let's go ahead and go into my thing, and then I can hard code this number to that, and but make this so that by the time I execute it, it doesn't already elapse. It was 5. I'm going to put it as 6. Okay. I hope that is not too late, but maybe let me put 5 here and make this as 9. So that is some time in the future. You agree? If the current time was 459, I changed it to 959, so that's 500 seconds. I don't know how many minutes that is. 700 seconds is maybe too much, but we'll see. I will come back and change it to something closer to get it to work in a little bit. So what does this do? So this number, when if I come in and if come in right now and then try to compare it, this assertion is going to fail, and I won't be able to add the person. So this function is very much similar to what you have seen, except the assertion, instead of looking for ownership, it is looking for the start time. Okay, so and this is keeping track of the, instead of like an array, it is keeping track of people in this hash map. All right, now let's go and get and compile this and compile and come here and first clean out all the garbage and make sure that we don't get any error. So we keep track of that here, and we'll clean this out. So I'll clean, deploy. All right. Now the deployed contracts at the very bottom, which is hard for you guys to see. Now I'll scroll up. Now if I try to add a person, so what we have been trying to add a GIAN course. Let's try to add this thing here, and then it failed. Why did it fail? We didn't change the owner. The person who deployed it is the same person who is trying to add the person, add person here. The issue, the reason why it failed is because it failed this assertion. Okay. So because if you look at the current time, the last 5 digits of the current time, this one is saying that this needs to exceed 5959, and it is still 5459. Yeah, it is still 5459. Right? Actually 5635. 5635, I refresh the page, 635, and it is getting closer and closer to this, but until it exceeds this value, this you won't be able to add a person. 5959, let me see how long it's going to take. I want to see if I could make it so that it's 5658. Let's make this make this 7, and then I still have to go through and compile and deploy. First clean out, because I don't want to get confused with the old version, and open the contract at the bottom, scroll up, add person, and so I will just simply put A, comma B, and add person. It failed, it still failed, right? And that's because it is 5759, and what we have here, 57. It's getting close, right? In 1 minute I should be able to execute it. Okay, I'll just hold off. All I need to do is I need to wait until it becomes 5759. Let's refresh this. Actually, I can see it right here. I don't have to keep refreshing. You guys are following what I'm doing?
Yes, sir. Done, sir.
Now I should be able to execute it, right? So if I go back and add this person, and that's green, right? So it's exactly what we wanted to accomplish. So, so you can set your time bounds here and deploy this contract on Ethereum, and that it is like a timer, and when the timer comes alive, you can have it do certain action. So this, this is an add person, is you have to manually add it, or In this particular case, you would give the tenant's address the ability to, only tenants should be able to hit this give me the code function, and then they would give me the code, and they'll be able to retrieve the door code as long as it is after February 28th midnight. So that's how you could apply this this kind of a smart contract. Any questions on this? Okay, there are no questions. Let's go on. Keep marching on. Let's go to File Explorer. We covered first, second, time control, access control, arrays, inheritance. Okay, now let's take a look at how to buy a token. So what does it mean to buy a token, and how we can accomplish that? And let's get rid of all these other ones. And we don't need this. And so the concepts here, we are going to use this new data type called address and address payable, and how that is can capture certain values of tokens. Very, very small program, so I can actually get the whole program on one screen. We're going to ignore the top two lines, and I'm going to compress this, and now it is just that. Okay. Again, like I always do, I look at the contract. Here is the beginning. Here is the end. I go right away to how it's getting initialized. Okay. So how it's getting initialized is that now this is expecting a parameter. It's expecting me to supply a parameter that's an address that is payable type of address, and I will show you what that looks like. That name of the parameter is called _wallet, and I am going to store within a private variable called wallet within this contract. The contract looks like a class, right? And here we have balances, and that balances is a public variable, and it's a it's an associative array. Interestingly, this time it is not going from unsigned integers to unsigned integers. Instead, it is going from given an address, it will tell you how much balance that address has. Okay, so that associative array can be, we can look and say, hey, how much my wallet has? How your wallet has $10 or what have you, right? So that's what this variable is going to keep track of. It's an associative array, and then given an address, it will give you an integer. The integer is presumably like how much currency you're holding in that address, at that address. Okay, so how is this a buy token? So this is the meat of the contract. This is all there is. It's a public function. Anybody can call this, and they invoke this as a buy token function without any parameters. And then what that's going to do is that it's going to increment the moment they hit the buy token button. They grab who the sender is. They'll get their address, right? Because it has to be, look at the associative array key value. The key value happens to be an address, and the way it is retrieved is by looking at who is invoking the function. And that balances for that particular address is incremented by 1. And the assumption again is that these values are all initially 0. Okay, so because in the constructor you don't see them initialized to 0, but the assumption is that they're all initialized to 0, and you take that 0 value and increment it by 1 initially. You come back and execute it again, it goes up by 2, and so on and so forth. And then you take the wallet, which is a payable address payable by wallet, and then you transfer the message.value. So this has this function called the transfer. The address value has a function called transfer, and you look at how much money came in and you transfer it to that to that person who invoked this function. All right, let's compile this and execute it. Compile by token. And so there is no issue with that. Now let's go ahead and deploy it. Before we deploy it, let's clean out this stuff. And then make sure that we're not getting any errors. And I want to clean this out. Okay. Let's go ahead and deploy it. What happened? So what happened here? It failed. Why did it fail? Remember what we said about this particular contract. In order for you to deploy it, it is expecting a parameter, right? And it is expecting an address, right? So that we need to provide an address, and that where are we going to get that address? Because if you look at this constructor, if you want to call this, if you want to deploy this, you have to provide the wallet address. Where are we going to get this? Well, the way we're going to get this is we'll go down here, and these are all addresses. These are all wallets, right? These are all accounts. Wallet and the account are the one and the same thing, and I'm going to copy that. Then I'm going to paste it here. Then I'm going to hit the deploy button. Now it worked, right? So you can see the green thingy here. So this worked. So that's going to receive. That is the wallet is going to receive whatever message is sent. Now, if you look at, let's go down here. I can keep querying this address. This is the key, that the address what I provided, right? So this address is what is going to keep increasing its balance. And if I hit buy token, it worked, right? No problem. And if I hit balances, sure enough, you see 1 here, right? Balance went up by 1. And if I keep hitting buy token, balances 2, and then so on and so forth. Right? So we could do this from a different account, and we can put in some values here and try what happens. Then buy token, and you can look at the balances. But now we have to give the new address because I went to a different account. So copy that, paste it. So now this person purchased 1 coin. Okay. So this person transferred. You can see that this person transferred 5 ethers, and that's 5 times whatever the 10 to the 18 be. And then you can see that the account value dropped down from 99.999 to 94. That 5 got transferred to the first account. All right. That's how they spent 5 ether and purchased 1 token coin. From the money got transferred from this account to the first account, which is that starts with 5B3 account. This is how coin purchase is made. Any questions on this? So these are all functions that are unique to addresses. So with the address, you can transfer the value. So you took that address. Wallet is, what is wallet? Wallet is of type address, and it is capable of receiving money. And so it took that wallet and it grabbed that 5 ethers and how do we know it is 5? And it is inside this attribute in that MSG. And then who should it grab that 5 ether from? This is the sender's address, and it subtracted from here that 5 ether and added this 5 ethers to this current wallet, which is the wallet that actually deployed it, because this is the wallet that actually deployed the contract. Questions on this?
No questions are flowing through, Professor.
Is this clear, Karthik?
Yes, it's quite easy for me to follow.
Okay. So these are the types that you don't find them in typical programming languages, like such as what is a wallet? Wallet is basically an address, and it has a certain built-in functions like transfer. And this message is simply asking, who called this function, and that gives you that address, that hex address that I showed you, and then how much they are willing to pay for the coin. And so these are all the values were in our deployed. So this would be an address of the wallet, and they put in saying that, okay, I'm going to give you 5 ether, right? So and so on and so forth, right? And
incidentally, Professor, I was also working on the same Git project for the tutorial session from this GAPP University, the URL that you have sent. So,
okay, perfect. DApps.
Yeah. So I'm able to follow it quite easily as I have
Yeah.
already gone through this.
For somebody who has not seen it before, some of these things are a little bit confusing. Well, mapping is very simple, like a hash map, but what exactly is an address? How can address receive some things of certain value? But it is just, these are just numbers. You just associate certain numbers with certain accounts. So with this hash value, you just associate a certain integer. Initially, it started out with 100, it went up 104, and so on and so forth. Yeah, so I think maybe it's easier for you to understand. I don't know how many others are following it who are in the audience.
Maybe in the tutorial session in the evening, Professor, I think we'll actually go through the blog step by step, and we'll try to do a hands-on.
Wonderful. Okay. Okay, so let me get my file explorer. Yeah, let's take a look at events. I think next. And I'm going to suppress this. I'm going to suppress that. Okay, we don't need buy tokens anymore. So events are, because this is an asynchronous system in the sense things are happening without coordination. Like the example I was giving you on that midnight, February 28th, something comes alive and then it allows a gate to open. These are asynchronous, and there can be some use for having messages and messages associated with different events. Incidentally, there are no print statements. If you need to really debug anything, you would have to create these events, send messages, and look at that debug log to figure out what is going on. So receive is an external modifier common pattern in Ether to smart contract, and it executes what's called a default function. I will show you what that is. Events inside smart contracts can be subscribed to by external consumers. So we can say that whenever it is sort of like saying Warren Buffett is one of the most famous investors here in the US. He's amassed a big fortune by investing wisely in stocks and bonds. And so you might want to put a trigger saying that whenever Warren Buffett buys a certain stock, I want to know what that stock is, right? So something like that, something similar here. You can set up events and let them trigger when a certain event happens. Same thing. We start here and end here, and I go straight to the constructor to see how I can invoke it. This is how this is my entry point into the contract, and this also is expecting an address, just like how we supplied my address, and it's I'm going to call that variable as wallet. That's my wallet. This has not changed. It's the same associative array that is keeping track of balances. And here you have instead, when a purchase happens, we added an additional code that I have highlighted there and here, right? And let's see, I cannot select the control, hold the control key as well as there as well as here. Okay, so very simple, just like the previous one, nothing much changed. But here there is a default function called receive external payable by token. I don't think I could. Okay, so the way that the link I showed you, he uses a compiler version that is 0.5. And it looks like every time they go from one version to the other version, there is no backward compatibility. So I just wanted to, I took the examples from Remix, and since the current version is at 0.5, I said, well, let me just go to 0.7 because I don't want to be learning something that is old, right? And I figured I'll just choose 0.7 to be a good target. But much of the code that he gives you doesn't quite work the way, if you just copy and paste it won't work. You would have to try, do some trial and error to figure out how to get it to compile. So in any case, the real novel things that this particular program to pay attention to is this event purchase. And this event purchase gets triggered whenever that public payable function is called. And that is, it emits this event called purchase message dot sender and 1. And so this is the buyer. So this is the address who is buying it. This is and how much they are buying. They're buying 1 coin. So what putting this indexed that modifier here for this variable does is that it lets you filter, saying that so if there are a whole bunch of purchases happening for the coin, like I was the example I was giving you, I only want to listen to, I only want to subscribe to the purchases made by Warren Buffett. I don't want to look at every Tom, Dick, and Harry buying coins. I'm not interested. So this allows you to do that kind of a filtering when you have that like that. But other than that, everything else remains the same for the most part. There are only really 2 things: the purchase event and a call to that. Okay, this shows you how many coins were purchased and who purchased it. Okay. If I were to compile this, luckily it also passed the compilation check, and this is already okay. I want to go in here and clean this, and then go to my deployment pane and clean this. And so I want to go back to my first account. This is my account, I'm assuming. I'm the one who is deploying it. And if other accounts want to come in and purchase it, that's fine. I'll make money. And then I'm going to go ahead and deploy it. And it's going to fail. It's for the same reason that we failed the first time. I keep forgetting to give the parameter for the constructor. It is expecting me to tell who is the one who's actually launching this coin sale. Right? I'm going to copy that, put that address here, and deploy it. Oh, it still doesn't work. What happened here? Should be payable if you send. Okay, so let's clear this. Okay, now it worked. I don't know what happened there. So in any case, now it got deployed. I open it down here, and then I've got the buy token and the balances. So if I go back again and I can, so if I keep buying myself some tokens, that's not interesting, right? Why would I want to buy my own tokens? It is not very interesting. So I will change the account up at the top, and I'll make it the second account, and then I will make him pay again 5 ether, and I'm going to say buy tokens. It worked, and then I want to find out, well, I paid 5 ether. I want to make sure that I received the coin that I paid for. Go down here and check. Sure enough, I got my one coin, and hopefully the balance got deducted from mine, and it sure did. It went down from 94 to 89, and this bank balance went up from 104 to 109. Okay, so no surprises here. Everything worked the way it was working before. So just because we added events doesn't mean this it's going to stop working. But now what good is this adding these events? Where can I see these things? So what you can do is that whenever the transaction happened, you can open this. This is what I was telling you. You can use this messages also for debugging purposes, and you can look at the logs and say you can see who the buyer is. This is a second user. I don't know if you can see it now. You can probably see it, right? It's the second user, not the first user, right? And how much did this person pay? So this person paid 5 ethers. So this is 5 times 10 to the 8, right? So that's it captures this information from the events. You guys have any questions on this? So let me clear this and bring it back to normal level. Open the file explorer. We're almost out of time. So I covered this, I covered time control, I covered buying a token, I covered access control, I covered events just now, I covered arrays. There are these are only 2 things that are left over. Actually, both are a little bit complicated, because what happens is that you are deploying 2 separate contracts, and one contract calls another contract. And I don't believe we have enough time to go into them. I tell you what we could do. This, let me just quickly show you. This shows you polymorphism. It shows inheritance. We get rid of all these things. Okay, there is inheritance and there is multiple contracts, and it shows you how you can have. This is actually maybe a single contract, and we can cover this fairly quickly when you come back from lunch. This shows 2 separate contracts in the same file. Let's make it go away, and I'm going to make this go away. And you can see that there are actually 2 separate contracts. There's one contract that ends here. There's a second contract, and they interact with each other. And it takes a little bit of time for me to actually show you what those are. Why don't I cover these 2 programs when you come back, and then I will quickly say a few things about how to build a gold exchange using permission blockchain. And that will be that for today. Yeah,
Sure.
Yeah, it's
Sure,
good
sure,
question.
Professor Ramki. We'll reconvene at 1:45 then. Thank you.
Mhm.
Prof. Ramki, we are awaiting some more participants to join us. We'll give them 2 more minutes and then we'll commence.
Absolutely, yeah.
Thank you. Uh, Professor, we can commence the session.
Excellent.
Floor is yours, please.
All right. So, welcome. I'm going to welcome everybody back from your lunch. So, my goal is in the next hour or so to just wrap up where we left off. I'll just show you one more Solidity example. And then I'm going to save the time to cover on gold exchange, how permission blockchains can be put to use to, it's like a proof of concept gold exchange. It is far from a real exchange, but I'm just going to hint at what the advantage of having a replicated state machine, what's called a replicated state machine, how that comes as a result of having a consensus algorithm, and how that can be put to use to build an exchange. So I want to cover that. So let me just go back to this screen here and show you one with the multiple contracts, and the inheritance one is fairly simple. That I let you look at it on your own.
Professor,
multiple
your slides are not shared yet.
Okay. Yes. Enter screen, share. There you go. Okay. Now you can see it, right?
Yes, please go ahead, sir.
Yeah. So this is the same example. This is the purchase of a token between two parties. So to simulate that, from the 20 accounts I have been using first two addresses. The first address is the one that is selling a coin. The second address is the one that's buying a coin. So we take the previous example, how to purchase a coin, and we're going to refine it so that the minting process and the token is extracted into a separate contract. And the couple of things that are worthy of mention here, when you see here ERC20 token, so what that is it is an Ethereum standard. So if you build something on a crypto exchange on Ethereum, and you want to start monetizing that to raise funding for your company or what have you, then it needs to comply with the ERC20 standard. They've created a standard. Basically, that standard simply says that, well, the coin needs to have a value, how many you're printing, and or how many you're minting, sorry. And there are certain attributes. It needs to have a symbol, it needs to have a name, such. So it is like an interface, like a Java interface. Java interface requires a certain functions be implemented. Much like that, ERC20 is like a standard that is put together by the Ethereum Foundation. So this is nothing to do with that standard. It is still a toy example, but the goal here is that if you ever were to implement real crypto, you would separate it out into a contract like that. Well, now I have two contracts, right? What happens when I deploy? Do I deploy one? Do I deploy both? If so, then how do they interact with each other? All this makes it a little bit more complicated than the example we have looked at, but not by too much more. So let's apply the same principle that I've always used. So this doesn't even have. So let's look at the start and the begin of this token. That's the ERC20 token is the name of the contract. It doesn't even have a constructor. So if you look at it, it's a trivial function. It has one string variable, and then it has this. Okay, now I'm going to ask again. I hope some of you still remember. What is this? What does mapping mean? What is this?
Assertion.
Associative array. Excellent. Okay, so somebody is at least paying attention. Associative array has a key, which is an address. The address is the hex values I've been showing that I copy and paste. And the value given for a given address, like the first address that I've been using, it will give me how much balance I have. I had 100, it started with 100, and I received 5 tokens from the second account. I became 105, 109, and like that, right? So that is the second value, key value pairs. That's what this keeps track of. So they can think of it like an abstraction of a wallet, right? So for a given address, it tells you the wallet balance. And this one keeps track of the balances, the function mint public, and then it looks at the transaction who called this, and it sets that origin. It increments that the number of coins held by that the origin address, by it increments it by 1. So nothing changed there. Okay, so and coming down to this contract function, this has gotten simplified now. It has a constructor, but now there is something interesting going on here. So since there are two contracts, when you deploy them, you have to deploy both of them. So I need to know where this other contract is, and I'm going to capture that address in the second parameter of the constructor, and I'm going to keep track of it. If I wanted to mint a token, I would go to this address given by this token address, and then I will say use the token value and then mint. I'm going to invoke this function mint. That's the purpose of having a second parameter in your constructor. Otherwise, this guy gets paid in cash, in Ether. So this is the recipient of the transaction. So in exchange for minting a coin and giving it to this address who is calling this, you would get some Ether, and that gets stored in the wallet. So that's how the constructor has changed. The only thing that has changed here really is an extra parameter called this address, and that gets saved. This is the address of. This is not the address of the person who is calling. It's the address of the smart code contract that you need in order to call the mint function. If I want to call the mint function, I need to know where this contract is stored. And that is this address that you see here. I hope that's clear. And so I keep track of that, and I use that token to. And so this is how I use it. I create this address token, and I call the function mint. Okay, so in fact, you don't need to do it. You can actually simply write, instead of those 2 lines, you can also simply write it like this. Call this smart contract ERC20 token, and here is the one that is deployed at, and then using that, mint it. And once you have that, you transfer it to the wallet. Now let me see if I can compile this. So let me go into the compile window. Let me hit let me make sure that there are not any errors here. Let's hit the compile button. That compiles great. And then now I want to make sure there's nothing here as far as deployed contracts go. Now look at what happens if I just try to so when I go to the deploy, there is like choice here. Right? So this is my first account. I am the owner. This is my primary account, and I am this some secondary account from which I've been receiving ether. That's why my balance kept going up to 116, and this person's balance went down to 82.999, whatever. And so now, if I try to deploy, I'm going to get an error, and this is expected because it's expecting some couple of parameters for the constructor, and I have not supplied those. Parameters. Well, that begs the question, where am I going to get these parameters? So what is it asking? Remember, this is asking, when you sell a coin, you're going to get some ether. Where should I put it? So it needs the address of the wallet. That is my address. It's right here. And it's also asking, where is the coin smart contract residing at? Well, we don't have this yet because we have never deployed it. We have not deployed the ERC20 token smart contract. So I think so. The order in which we need to deploy them, we need to get this first. Let's go ahead and deploy that, and that you can see that it clearly worked. Now I know where that smart contract is, and so where is it? It's down here. I don't know if you guys can see it. I'm going to open that, scroll up. And so I'm going to copy the address of where this smart contract resides at. So I'm going to copy that. Now I go back and now I am ready to deploy my main contract, right? Now the smart contract, the second parameter I know. So I'm going to paste it before I forget. And the first parameter, I'll go to the front and then put a comma and then insert the first parameter, which is my wallet, so which is at this address. So I'm going to grab that. So I want to make money selling coins. I'm going to put it down here and paste it. Now I'm going to try to deploy the second contract, my contract here. So let me hit that deploy button, and it worked very well. Now, excellent. So what do I need to do now? So this is the first contract. I don't need that. It's the second contract is what I'm going to expose to potential buyers. And when somebody comes and hits the buy token, and I want to make sure that it's the second guy. This is the guy who's been buying my tokens. So I'm going to pick that guy and say this time, how much the balance does he have? He has 82, right? Let's say he is willing to pay 7 ethers. Okay. I don't know why it gets erased. This IDE is not the greatest, but it works. And so he's willing to pay 7 ethers, and then we will go ahead and buy the token, and that worked also. And so you can open this out and see, and the fields are going to show you how much you got, who gave it to you, so on and so forth. And this should get deducted by 7. Sure, it did. And my thing went up by 7. So all looks good. Right. And this guy needs to make sure that he received the coin, right? So you copy that, and then you can go into the balances, and then you put down the address and say, hey, tell me, did I get my coin or not? And sure enough, there is this coin right here. You can see that, I hope, right? One of the coins was sent to this address, the one who purchased it for 7 ether. So that's how multiple contracts can be also. Now this is how this Solidity contracts interact with each other. So each contract has an address when you deploy it, and you use this address like so, and invoke the appropriate function. In this case, we are using it to mint coins. And so that's how this, it's mostly this is the one that calling this, but you never have this calling that. Right? So you don't have the first contract calling the second contract. So that's how multiple contracts interact with each other. Is there anything I want to show before I close this out? Yeah, there's only one other one I was going to consider was this inheritance. It's really not that interesting. I'll let you read it on your own. So I have, so we spent 15 minutes. I have about 45 minutes to cover the gold exchange. I think that's enough time. Any questions on this multiple contracts?
Professor, actually, some variables are annotated with this memory keyword, right?
Yeah, so only the string variable.
Okay, so
The string
can they
variable, not
understand those variables, as you know, the ones which are not persisted on the blockchain?
Yeah, so those disappear. I think those are like ephemeral variables, and I believe these are the ones that are going to be persistent. And so this is also something that is a requirement that came in the newer versions of Solidity. Before, like when around 0.4 time, you didn't have to put this down, but now the Solidity insists that you put this down specifically. I haven't done enough research to find out exactly what the reasoning behind that is. But for strings, you do need to have that. Otherwise, it won't even compile. So it has all these oddities like that, right? So several things like, for example, if you put a constructor and you say that public here, though this is understood, why it won't compile actually. So compile inheritance. So it has an error here, right? So if you put a constructor and put public, which used to be fine a couple of versions ago. If I change this version to say, I don't know, 0.4, and then change this here, go down to one of this, then you might not have a problem, for example. So if we compile this, maybe that still has issues. I thought maybe you have to go even further back. And so at some point they said, well, you can't have that. So things like that, there are some oddities like that I've noticed in this language. Like, for example, if you follow that tutorial that I pointed out, right? I think I removed that actually. If I do this, I'll get that back. If you follow and if you just copy and paste, unless you actually use his version number, which is 0.5.2 to compile, you will get compile time errors. Actually, well, so he does have, actually, if I recall correctly, I don't know how he's able to get away with putting public for constructors, and that's one of those things I had to go through and remove. If I put public here and choose for, is it, so I get rid of this, let's say 4.0.4.2, is it 2? What does he have? Yeah, there is it, 2.4. And if I choose that, and if I compile it, I hope I still get this. No, I get a different error this time because this virtual keyword was added later. So I have to remove that. So this has all these kind of issues with. So I think this needs to go to. Now we do. What happened now? There is some other. Oh wait, so this just like how we explicitly stated it is public, and you need to say this for this constructor as well. So where does it go? It goes at the very end before the curly brace. So it goes right here, I believe. How it works. See that? So it's very finicky about this things like this, and you can see there are so many compiler variations here that you have to get that right. So unless you copy everything from some, it's not going to work. So that's very important. So now I got it to work, and you can go to for the execution part. There's no issue, but for compilation, and so string memory is one of those things that got added, and for the life. I mean, I've never really tried to research it. What was the rationale for adding it? Just given all these oddities, all these odd things about the language, I said it may be one of those other things like that. And so. All right, so let me move on to just change gears, and I am going to close this out. I don't need this anymore. Leave the site, yes. And then I go to my PowerPoint presentation. And so if I do this and gold exchange, okay, excellent. Then go into the,
sir, one.
yeah. Go ahead and ask the question. Yeah.
Sir, yesterday for blockchains like paraceuticals and food chains, some were actually implemented.
Provenance, right? Yeah, for provenance. Yes. Yeah.
Like food chains, use cases.
Yeah.
Like for these smart contracts, like anyone implemented like this, IBM implemented, you said.
Yes. So they only these are all proof of concept. So none of them are, to the best of my knowledge, none of them are there in production and making money for IBM or for any company. To the best I know. So that even this Everledger company, I don't know how well it is doing, but the one that keeps track of the provenance of diamonds, right, from the mine to the jewelry store, it keeps track of every step and ownership changes. I don't know how well they're doing, and so these are all like this. They look like they're good applications, but I don't know if they really have gained any traction in reality. So what was your question anyway?
No, sir. Yesterday, like food exchange, you told no, sir. Whatever.
Yeah.
Same applications like it was implemented. Any use cases? Let's.
Are you asking whether there are any use cases have been in production?
Yes, sir. Smart contracts.
No, there are only proofs of contract. There is proof of concept. So they just run a pilot, but they say, yeah, this can potentially be done. But they look at the costs of doing it, and they look at the weaknesses, and then decided not to pursue to do it commercially. So those are just like like I said, like a pilot tests, and nothing is there in reality.
Sir.
Okay.
Okay, sir.
It's like, say, what are the applications of this new technology, and people just give these examples again and again. But if remember in the very first day I said, I don't know when was that. I had a Reddit headline. I took a screenshot of it and pasted it. And this is, you guys know what is Reddit, right? It's sort of like a discussion group. People have like interest groups, like, it could be crypto, or it could be vegetarianism, it could be global climate change, So you pick a topic like that and you participate in discussions. And in the crypto exchange, somebody just wanted to have a debate, saying that he posted this inflammatory headlines. They said 99% of crypto has no real life utility. Prove that I am wrong. He challenged, right? And the reason why I put that in my slides, and I believe it was the very first day that I had that. If you go through and you'll see it, is that I still believe that is the case. You look at, it has what we looked at Ethereum market capitalization, right? And it is also like several $100 billion. Market capitalization means, so if I go around trying to buy every single ether that is out there, that is in circulation, that is held by people, right? If I go try to buy them, I would have to spend several $100 billion. This is more than buying every single share of Oracle. It is like more expensive than buying every single share of IBM. So that's the kind of market capitalizations these cryptocurrencies have. And so you would wonder, that goes back to the weight of the cow example I was giving you, or the cutest animal podcast thing I showed you. You should go back and listen to those things, and because it's not that they have any utility. They think that other people think that has utility, and so they go ahead and squat, and they go ahead and take the coins and wait on them to get appreciated. And that's what people have done with Bitcoin. So that Reddit post is accurate. It doesn't have any real life utility, but people are speculating that they are going to have a lot of value in the future, and they should just buy and sit on it. Going back to your question, so does it have people? Does IBM, has it really implemented the food chain network? I don't believe so, but they always use it as in their marketing literature that it can be used there. To the best of my knowledge, I don't think there are really production use cases for all these examples that people give. There may be a few the only example that I can think of is cross-border payments. So if I want to send dollars, equivalent of dollars to India in rupees, and I don't want to use traditional banks like Western Union because they're expensive and they're slow, then that market is slowly opening up. That's about the only example I know. So that's a long-winded answer to your question.
Okay, sir. Thank you, sir.
Okay. All right, let's take a look at what does it take to build a gold exchange. And so at the heart of a gold exchange is what is called the notion of a replicated state machine. And what a replicated state machine, I am hoping that most of you know what is like a finite state automata. So finite state automata, there are inputs, and based on the input, you go from one state to another state, right? So that is called a state machine. And in a very abstract way, a computer or a log, so the thing that you see here in the green here, can be thought of as an automata. Okay. So, like, what is this automata made of? So this hash map that you see here, the key value, the associative memory. So you have three variables x, y, z, and then they can take on different values. X can be 1, y can be 2, and z is 6. So the reason why the adjective replicated is here is that when these variables change values, because some client says that change the value of x to 3, okay, and then there would be 3 here. Later on, somebody comes along and says put value 2 in y, and then there would be 2 there, and some other client comes along and says that move value of 1 back into the x variable. So 3 gets erased and 1 goes up here. And finally, somebody puts the value of 6 in the variable z, right? So these things are coming, these requests are coming, these assignment values are coming from different machines. The challenge for a replicated state machine, so this is undergoing state changes, right? So x comma 3 was the original state. In the new state, it is x comma 1. Same way, maybe before y was undefined and y became defined to 2. So it changed state, right? So there are infinite states. You can think of them as because you can possible values that we can put into the x is infinite. Same way, this can be infinite and this can be infinite. And if you take the Cartesian product of these three things, that's a big infinity, right? So it doesn't matter. But the key is that whatever state this server is in, you want this server to be in the same exact state. That is the challenge that needs to be solved. And this also needs to be in sync with all these things. Well, there is a very simple solution to this, right? So when somebody comes and submits saying that change the value of x, and then in an ideal world, you take, actually this is a z assigned 6 value. Let's take that as the example. You want to assign z to 6. This client comes and says, put 6 in the value z. And say, okay, fine, I'm going to do that. But first I'm going to inform that this guy needs to change it to 6. This guy also needs to change it to 6. Okay? And then he expects a response back saying that I received this message to request that the z be changed. So I know this server has responded, and I know this server has responded. And now that I know that they all got the message, I can go ahead and I can go ahead here and change the value of z to 6, and then let the client know that I successfully changed it. Not only here, I made sure that it is changed here and changed here, right? It looks simple enough. What's the problem with this? Why can't we accomplish this? This is important enough for me to actually wait until somebody gives me some answer. Why doesn't the algorithm I just described, why doesn't it work? These servers, by the way, they are not sitting on a local area network. These servers are separated by continents. So this could be like in Africa and the US and Asia and so on. So they're all separated. So what's the problem in accomplishing, maintaining the same state? That they're an identical state. Why is it difficult? Take a guess, and it doesn't matter. You can unmute and say it, or you can type it in the text box there. The question is fundamentally, I have these geographically separated servers. They're trying to keep the value of these variables identical in all these locations. Why is that a hard problem? And I just shown you, like, to follow those red arrows. So before you change the value of z in the rightmost server, it informs it. The other two servers waits for the response, and then commits the value of z to 6. Why doesn't this work?
Participants, please feel free to unmute and just you can share your thoughts. We are not expecting the right answer.
There is no right answer, wrong answer. It doesn't matter if you say something. You can think aloud.
Actually, there is one tangential answer flowing through the chat box that says security.
It has nothing to do with security, actually. Because security, well, security could also play a role. But okay, so let me change the question, saying that we'll assume that there are no malicious actors in this scenario. It is, it is not a tangential. I would say this could potentially be a good answer, because if there is like a malicious actor trying to sabotage this communication channel and blocking all these messages from going across, then these guys don't know that the value of z needs to be 6, right? So it is a correct answer, but I'm going to change the question by saying that now let's assume that the people who are participating in this protocol are all vetted participants. They are good people. Imagine a wide area network.
Professor, I'm hearing some murmuring from the people who are sitting near me, which says
Okay.
ordering of messages.
Ordering of messages. They're looking at the bullet points, but the bullet points don't reveal the answer, actually, what the challenge is. Yeah, so we want to make sure the ordering in which these variables change is the same at all these servers. And how do we accomplish that order is identical? So this green thing you see at the bottom, it should look identical so that they can consume this input and change the variables accordingly. First change x to 3, then change y to 2, then change x to 1, then change z to 6. These are all the ones that requests are coming in, and those requests are collated or are sorted so that they all are in the same sorted order at every single server. Why is that difficult to achieve? And we will assume that, like I said, there are no malicious actors, like monkey in the middle kind of thing, where monkey is coming and ruining it for you. Let's assume that is not the case.
Professor, some more answers are flowing through.
Okay.
No loss of data, even in case of system failure. That's one answer. And another answer is faulty system or failure.
Exactly. So finally, okay, so somebody just gave the correct answer. Remember, if in order for this the rightmost machine server to commit the value z to 6, this is very similar to the two generals problem, right? I sent values, hey, change the value of z to 6 to the middle guy and to the left guy, and then I need to know that they got my command. And so that means they need to respond back saying that, yep, we're going to go and change the value of z. And this in real world, in a wide area network, when the machines are separated by multiple continents, some of the servers could just die. The messages could disappear. Right? And in the absence of that, just like in that the two generals problem, in case of non-Byzantine faults, it is difficult to make progress. That's what makes the problem difficult. But that is what Leslie Lamport has solved, and he said that as long as you have a simple majority of servers up at any given time, right? So if you have 5 servers, A, B, C, D, E, at any given point, as long as you have at least 3 servers up, it could be ABD right now, ABD, and 5 minutes later it could be B, BDE, after that it could be ACE, it doesn't matter. But at any given point, as long as you have at least 3 servers, you can guarantee progress. So if this machine goes down, when it comes back up, before it goes ahead and changes its state in this pink table here, it goes back and say, well, my log is corrupted or incomplete because I died. And so it goes to the other machines that were up and tries to learn what the set of commands that it should have had. And it learns that, and only when it is sure that it has at least correct partial log, and it starts applying to the state changes, and eventually it will catch up, and the state here will become identical to the states here. So that is why this is called a replicated state machine. So you're maintaining a finite state machine kind of thing here, and that's replicated across multiple machines. And achieving that is highly non-trivial, and that's what you need these algorithms like Leslie Lampert's or Raft or any one of those. In fact, this figure actually is from one of the Raft documentations. Okay. So the thing is, all servers executing the same commands in the same order. So that green thing, you see that? Assign value 3 to X, assign value 2 to Y, and so on. They're all identical between the machines. All servers are. So if they start out in identical initial state and they apply identical set of instructions, of course they are going to be in identical states. Right? They are going to be in replicated states. So as a result, they'll get an identical state changes at every server. So we're assuming non-Byzantine, and we're going to assume that at least half of them are up at any given time. And that's the problem that Leslie Lamport solved, and that goes by the name Paxos. Okay, now that you understand the basics here, now let's go to the next question. How do I build so before you look at these diagrams and these trees and all these things, let me ask you this question. How do I build a gold exchange that spans the entire globe, where the servers are in different continents? So actually, I have given you a hint by just showing you the next slide. Basically, at a very high level, this is an exchange. It's a marketplace. What we have is we have sellers and we have buyers. So this is we don't have this variable assignment like this. Instead, we get a request to either to sell some gold or to buy some gold. Those are the only two kinds of proposals we're going to entertain for our discussion. And so when you buy or sell, and it is also the quantity, how much you want to buy and how much you want to sell, right? At an abstract level, that is what we want to. Those are the only kind of proposals that we want to entertain. So then any one of these clients can get that, and they submit it. So this just like this Z assigned 6 arrow, that these guys have some John Smith wants to sell 10 ounces of gold, and they submits it to this. This guy would take it and give, saying John wants to sell something here. John wants to sell something, right? So all of them would receive, and Paxos guarantees that they will eventually receive that, even in the case of faults. Okay. And when we get those sell orders and we get those buy orders, what do we need to make sure of? So I need to separate the two into two sets of buy order separately and the separately. Let me ask you this: if multiple people are coming and saying that I want to buy, I will just throw out a number. I don't know what the gold price is. Let's just say it is selling currently at $2,000. Okay. And you're getting all sorts of proposals. So one guy is saying I will pay 1800, and another guy is saying I'll pay 1850, and so on and so forth. Right? Who is the guy who is most likely to buy when they're bidding like this in the marketplace? Who is the one who is most likely to win their bid? They're bidding for this gold. Is the guy, you get all these proposals, and they're all over the place. This one guy is saying 1600 an ounce, another guy is saying I'll pay 1900. Who is the one who's going to win?
Whoever bids highest.
Yeah, exactly. So the max, right? Who you just look at all the proposals at a given time, and you want the guy who is bidding the highest is the one who's likely to get it. Let's flip to the side of sellers, and we said the market price is around 2,000. And I come in and say that I want to sell it for $2,400 an ounce. Will I have any probability of selling? Probably not, because I'm asking for so much more than what the market price is, right? And some other guy comes and says I will sell it for 2,200. Another guy says that I will sell it for 1,800. Who is going to succeed?
1800.
Yeah, and why? And what is that special about 1,800? Between 1,800, 2,100, 2,400, and what is special about 1,800?
Because it's lesser, we'll prefer.
It's the minimum, right?
Yes, sir.
So from the selling point of view, you want the guy who is asking minimum. From the buying point of view, you want the guy who is bidding the maximum, right? So we're going to separate the two proposals into two sets. The one who wants to sell, the one who create. All of you, I'm assuming all of you know what a heap is. Heap is a binary tree. These are two examples of max heap and a min heap. In a max heap, let's take a look at the right hand side here. If it's 100, this is a max heap. The biggest element in the set is at the very top, and that property is recursively respected at every subtree. So if you look at the max here, 19 is at the top, and the same thing to the right, and so on. So what happens if you need to delete this 100? Who gets promoted to be the root? So it's going to be one of his two children, right? Those are the highest values, right? It's going to be either 36 or 19. Right? So this guy is going to move up, and when he moves up, he creates a hole, and you have to look at the subtree here and look at the maximum there, and you have to promote the maximum to. So and then that's how it's going to percolate up. And then one of the higher one of these two children will occupy this hole here. So that's really how heap data structure works. This is a max heap. In the min heap, the flip side, you have the smaller of the two.
Just a small clarification here. If we do this percolate up the way that we described it now, won't that structurally affect the heap, because it's supposed to be a nearly complete binary tree?
Right. So there is some balancing, and that is really tangential to our discussion, and I will defer that to, like, you can click this and it will take you to a wiki page and it will tell you how deletions are done and all these things. And most, like Corman, Lyserson, and Rivest shows you how to do these deletions. So there is insertions and deletions. Now, insertion also kind of messes it up, right? And if you put in something big, then what happens? And so that's not really relevant for our discussion. Let's just assume that we have a binary tree that satisfies these two properties. And at any given time, the node is always in a max heap bigger or equal to than the two children. And in the min heap, how that inductively maintained, let's just assume that it can be maintained. And this I just took a screenshot from wiki page. And pasted it here. So finding the maximum, for example, is a constant time. All you have to look at is the root. This is about the max heap. And the delete maximum is log n. This is the percolation process I was telling you. Similarly, insertion process, when you insert something, it could disturb the structure, but you can still get it to balance it itself in log n time. And increase key is something that we don't need to worry about because we're not going to use it. There's a process called melding. Like if you have two heaps, how do you put them together? How to merge them together? And that's also something that we are not going to be interested in. But for the most part, and these are all the complexities of those operations. So we have a min heap here. That is like the property that's maintained by any node is that it is less than or equal to its two of its children recursively. And the same thing here with the max heap. So where would the buyers go? Do the buyers go to the min heap or the max heap? So buyers are all going to be in one heap, and sellers are all going to be in another heap, the other heap. So where would I put the buyers? I missed that one. Can you please repeat?
Through the chart window, they are saying min heap.
The buyer is going to be at the min heap. Okay, well, let's think about that, right? Let's go back to that example I was giving you. The market price is 2,000. Right? These are all coming to buy it. And the bids are, like I said, 1900, 1800, 1850, and all that. So if you put in the buyers in the min heap, where would the 1900 be? It will certainly not be at the root, right? You will have 1600 here because that is the minimum. And so if I need to find out who is the highest bidder, because I want to award him the gold that the guy is selling, he's going to be down here somewhere. I don't want that. I want to just consult the root and say, oh yeah, the highest bid I got was 1950. I'm going to give him the gold. And so if the buyers are going into min heap, clearly so that doesn't make sense to put the buyers in min heap. I would have to put buyers in the max heap so that if somebody comes along and said, you know what, the gold price is 2,000, I will pay 2,200. And I want to know who that person is in constant time, right? Because that 2,200 person who is bidding 2,200 will be at the top of the heap. And the rest of these guys are just noise to me. Some guy is saying 1,600, other guy says 1,500. I don't care about that. So I want to put the buyers in the max heap, sellers in the min heap. Because again, why do I care about sellers who are demanding a lot of money for their gold? And they are coming in and saying that give me 2,400, give me 2,600. I'm not interested in them. I'll put them below. And one guy says that I will sell it for 1,800. Yeah, I want him at the top. Then what can I do? I can marry this buyer to the seller, this seller to this buyer, and do a deletion of the root, right? And so delete max. In log n time, I can rebalance it and then conduct a transaction between them, delete and then continue. So that's roughly the algorithm for matching buyers against sellers efficiently. So this is heaps are implemented. So I've actually implemented this, and you can implement this in using Java priority queues. And you can also specify whether you are interested in a min heap or whether you're interested in a max heap. So you would have two such data structures. So let me go back to this structure. So instead of like a key value hash map, you would have a max heap and you would have a min heap, right? You'll have two such things, and all servers maintain both data structures and they keep them in sync. So when somebody gets deleted, it gets deleted in all servers. When somebody gets added, it gets added in all servers. And when somebody just matches off this root with this root, so that means that we found a match for between a buyer and a seller, you delete. The deletion happens at the same time in all servers, even in the presence of faults. So this is where you need to use a consensus algorithm like Paxos. And so this is where like a permission blockchain can apply, because people who are participating in this buying and selling gold, you have to make sure that you have to vet the participants. So this is like, I don't think I want to cover this. How much time? I only have 6 minutes left. So, I'm going to skip this slide because it is just same thing I just told you. It is written out like an algorithm. Instead, I will just go here. So this is the steps that one would take. So this distributed coordination that you see in the blue box down here, this is where Paxos makes sure that everybody gets a bid or an ask. The bids are the ones saying that I'll pay this much. Ask is so bid is coming from the buyers, so ask is coming from the sellers. So all these proposals are coming from all over the world, and so they go to the nearest server, and those servers take those things and they order them in whatever sequence, in some order, but whatever that order is identical. So this order you see here, agreement 2, agreement 1, agreement 3, and this is one server. You can think of this whole thing as one server, and there would be another server here and in a different country, and another server, and so on, multiple servers that make up a network. And so these order here in which they are executed that bring about the change in the states is identical in all the machines. Okay, so the heap, the two heaps, the min heap and the max heap, undergo changes in an identical fashion at all servers, and they would, if there is a match between the roots, they would match them, create a transaction, commit the transaction to the persistent storage here, and delete them, and then update the data structure. And every one of them, since they get this bids and asks in the same order, the heaps are going to undergo changes in the same order, and the transactions are going to get persisted in the same exact order. So if I run this code on one server and look at the ledger, and I look at the ledger from a different server from a different country, they are going to be identical. So that's how we accomplish this using a distributed coordination, even in the presence of failures. Okay, so the browser bid asks, so from the browser, the user is going to say, I want to either sell or I want to buy. And that gets queued up at the server, and the server dequeues it and submits it to Paxos algorithm or Raft algorithm, one of the two. And then it gets ordered, and that order is the set of commands is the same in all machines and all servers. The heap is modified here in step 5, and if there is a match, and then you match them and write the transaction to the ledger. All right, so the business logic, you have to think about. This is kind of a very, very simplistic it only just illustrates an algorithm how one could build it, but in the real exchange, you have to think about what is called partial fulfillment. If somebody, the buyer is willing to pay more than $2,000, say I'm willing to pay $2,200 per ounce, but I need only 1 ounce. And the seller, on the other hand, says that, yeah, that's great, I'm willing to take it because my ask was only 2,100. Since you're above what I was asking, I'm going to, but I need to get rid of 5 ounces. So then how the hell do you partially fulfill this match? So this is what's called business logic, and so different exchanges resolve this in a different way. In fact, if you have done any trading, and from my experience in talking to you guys, you haven't done any trading, you know how trade exchanges handle this. If I go place a bid saying that I want to buy one share of IBM, and I look at the browser and it is selling for $100, and I tell my broker, who is like Morgan Stanley or John Schwab or anyone, go buy, get me a share of IBM. Here is $100, right? By the time they get the message, they're getting ready to execute it. It might have dropped to $90. Then what are they going to do? So there are various ways to resolve this. One, actually, most of the time, if it is less than what you're willing to pay, they will get it for you, and they will pass on the savings to you. Another way maybe is to do is go to the especially in a distributed gold exchange, split the difference. Give 95 to IBM and let me buy it for 95. I'm buy it for 95. I'm happy because I saved $5. IBM is happy because they got $5 more than they were asking for, right? So how do you do this partial fulfillment, and what happens if the bid is more than asked? And what happens someday I put in an order and it makes its way to the heap, and then I said, "Okay, I'm not interested in selling anymore, or I'm not interested in buying anymore." How is that gets cancelled? And also the ability to pull the plug, and if the exchange, for example, gets hacked, somebody needs they need to just stop trading for some time, and that happens all the time. It happens during the pandemic in 2019 March. Because the market was dropping so quickly, they had to shut down the exchange. So how does one do this with gold exchange? All these questions are needs to be answered before a real exchange can be built. How exactly is gold kept? Where is it kept? Is it kept in like some kind of a warehouse? If it so, then how is it guarded? Who is coming or paying the cost of guarding it, and how is the ownership track? These are all the questions that in a real exchange need to worry about. So this is just a technical overview of how you can use consensus in the face of failures in a wide area network, message failures, server failures. In the face of that, how you can still maintain an identical heaps across machines and get a ledger that looks identical across different servers. So that's the idea. So I ran out of time. I'm going to stop here, and I will let you go to your tea. And after that, I passed on the slides to Karthik already, so he's going to distribute them. I will be seeing you in the conclusionary sections tomorrow, like the challenges and the future directions in the morning section tomorrow. But otherwise, have fun after your tea break, and maybe get to play around with the solidity examples and ask Professor Karthik how to do this solidity. Any questions on gold exchange? I know I ran out of time, going past my time. But if there are any question or two in the chat window, I'm happy to answer. There are no other questions. I'll be seeing you tomorrow.
Yep, Professor, there are no questions in the chat window, and
Okay.
we are happy to relieve you a little early today.
Yeah, that's right. Thank you.
Yeah.
Okay.
Thank you, Professor Ramakrishna, for joining us. We'll see you tomorrow.
See you tomorrow. Bye.
Bye. And participants, we'll just have a short break now, and we'll resume at 3 p.m. Welcome back after this short break. And during this session, we'll continue where we left off with respect to the elliptic curve cryptographic formulations. And in specific, I think we were discussing about how to formulate this ECC as a discrete logarithm problem. And later we will see how Diffie-Hellman kind of formulations can also be done using the ECC. And at the last leg of this lecture, we'll talk about the elliptic curve digital signature algorithm. That's the one that's used in Bitcoins. Okay. And after all this, we'll just take up the tutorial session on Solidity, and we'll try to follow the smart contract creation steps which the professor has shared with us, and we'll just try to do it in the tutorial mode. So this is the agenda for this 1 hour session. Just to refresh, during the previous class, we have seen the form of this elliptic curve, right? And maybe before proceeding, let me just confirm whether you can see my screen and hear me talk. Am I audible to you, and is my whiteboard visible?
Yes, sir.
Okay, thank you for the confirmation. So we were framing our ECC as a discrete logarithm problem, right? So where we are given with the elliptic curve. Let's say that E is this elliptic curve. And we are given with the parameters of the curve, right? By elliptic curve, we mean the coefficients A, B, and the P, the value of the modulus P. Okay, so all of these are given. And we are also given with the primitive point, which is the generator. So let's call it as P. This is the generator. So what we do is we formulate this as a discrete logarithm problem. If this is your elliptic curve, and let's assume that this is where your generator is, this P is your generator. What we try to do, right? We try to give a destination point. Let's say if this D is your destination point on the elliptic curve, you start from this generator P, and we try to find out how many group operations need to be done on this P before you can reach this destination point, right? So for instance, if you try to do the first group operation on this P, right? So somewhere you'll draw the tangent and you'll find out what is the value of this 2P, right? So let's say if this is where 2P is, and then again you will do the group operation on the second point, right? So this is your first point, this is your second point. Again you will try to do a group operation on the second point. Let's say somewhere you will land up here. The group operation is repeated here, and again you will come here, right? So the discrete logarithm problem on elliptic curve, it's like shuttling back and forth on the elliptic curve. How many shuttles are needed before you can actually get to this destination point? Okay, that's the the geometric interpretation of what we do when it comes to this discrete logarithmic problem on this elliptic curve. Fine. And figuring out this number of jumps on the elliptic curve before you can reach this destination point, it's really a hard problem, as we discussed in the previous class. And let me write it formally. So we are given with this generator P, and we want to repeat this group operation on this P some number of times. Let's say this value is I. And we want to reach this destination point D on the elliptic curve. And the public key here will be P and D. So this is publicly known. And this I is sort of the private key, right? So this is known only to the particular entity, and this is not widely disseminated. This is not known to other entities in the realm. So this is sort of the public key, and this is the private key. Given the knowledge of this public key, it's very hard for you to deduce this private key. That is the discrete logarithm problem. And the problem takes this form, right? So if this is I times, you can kind of write it like this. I times P, where I is the scalar, equal to D. Right? And it's very hard to solve this discrete logarithm problem. Just to demonstrate what I'm saying with the help of this elliptic curve equation that we discussed in the previous class, let's take this elliptic curve. This is y squared is congruent to x cubed plus 2x plus 2 mod 17. This was the elliptic curve that we were discussing. And if I tell you that the generator is 5, 1, and I wish for you to figure out this value of x that will take you from this 5, 1, let's say to this point 16, 4. Right? If you consult the table of values that we enumerated in the previous discussion, you can infer that the value of this x is actually 13. Fine. That will require you to apply that analytical formulation that we discussed about 13 times before you can come to this point 16, 4 and deduce the answer as 13. Right. This is doable manually because the curve is very small, right, and the order of the curve is also only 17. And which means, right, according to Hussey's theorem, the order of this curve, which is the number of points which are present in this elliptic curve, let's say if this O is the order of the curve, the number of points which are present in the elliptic curve, right, in the group that is formed by the elliptic curve, it's given by p plus 1 minus 2 root p. It's lower bounded by this, and p plus 1 plus 2 root p. This is upper bounded by this. And this is known as Hussey's theorem. And I'm just going to state it without proof because for me to prove this, it involves some sort of involved arguments, right? And that's also not required for our discussion. So roughly what you can see here is the order of the group is, like closely related to this number p. Higher the value of this number, right, the order of the group will also be higher. So for instance, as you had 17 here, we saw that after sort of 19 computations, we came back to the element 5, 1, right? So we got this identity element and then we came back to this element 5, 1 again. Okay, this happened after 19 computations, which means the order of the group is 19. This is 19 because, right, the prime that you are using here is kind of 17. And if you look at Hussey's theorem, the order will be within the vicinity of the 17. So in the elliptic curves which are actually used in Bitcoins, right, and in blockchains, the value of this P will be a very huge prime number. Okay, so that the order of this elliptic curve group is also quite big. That makes the discrete logarithm problem that more harder to solve. Okay, that much harder to solve. Okay, so the thing that we understand from Hussey's theorem is the order of this the elliptic curve, right? The number of points which are there in the cyclic group, it's roughly equal to this p, right? Plus or minus some correction factor, right? So this is on the lower bound, it's plus 1 minus 2 root p. On the upper bound, it's plus 1 plus 2 root p, right? So it's roughly equal to this p. Okay, so after having understood this Hussey's theorem, right, let's see how in practical applications we can compute this group operation on this elliptic curves, right? So this is what you find in typical ECC implementations. So let's say if I want you to compute some 13 times the generator number p, right? So this is like 13 times 5, 1. This means I'll have to start with 5, 1 and apply the group operation 13 times. Okay. Now that's a very analytically complicated process and computationally that's quite hard for you to do. So what we do is we kind of use this point multiplication algorithm based on doubling and adding, right? So this algorithm in the literature is called as double and add. Okay. So for this double and add algorithm, you are given with the parameters of the elliptic curve and you are given with this scalar with which you want to multiply this generator point. Let's say this I is the scalar, and using these two, right, we want to compute, generator is also input here. Let's say P is the generator. And using these three inputs, we would like to compute the value of I times P. The output from this is I times P. which means the output point that we get by applying the group operation on this p I times. Okay, that's the meaning of this. So let me jot down an algorithm and then see how it works. D is the destination point. Let me initialize this D to the generator point P first. And what I need to do, I need to just look at the binary representation of this I. Okay, so let me assume that this I has some T number of bits. Okay, so for I equal to maybe T plus 1 number of bits, for I equal to, let's say, the size minus 1 to 0, right? So S plus 1 bits are required to store I. That is the assumption that we have here. So for I equal to S minus 1 down to 0, what we do, I take this destination and I apply the group operation once on the destination. Okay, by saying D equal to D dot D. But if the bit at that position I is 1, right? So if, let's say, I'm overloading I, let me call it as J. Okay, so if the bit of this number I at this position J, okay, so if this is equal to 1, then what we do, we just take this D and we just add this point P to this D, right? I'll explain what we do here with the help of an example. Maybe after this looping is over, we return the destination point T. Okay, so this is the outline of this double and add algorithm, but I'll explain what I mean here. So let's say, okay, so let me take the generator point P to be 5, 1 and let the value of I is equal to 13. Okay, so the binary representation for 13 will be 1101, right, to the base 2. This is the binary representation for 13. I scan this from left to right and then I perform this algorithm as I scan this from left to right. I'll tell you how this algorithm works. So initially, in step number 0, right, which is the initialization step, I take this destination point to be P, which is the same as 5, 1. I don't do anything. This is just the initializer. In iteration 1 of that for loop, what I do, irrespective of the value of the bit at that position, I just go and apply the group operation on whatever is accumulated in the destination variable so far. Okay, so whatever is there in the destination variable is just P to begin with. So what I do, I just go and apply the group operation on P. Okay, so I compute this P dot P, which will give me 2P, right? Without bothering about the specifics here, right? Let me say that we get this 2P, fine? It could be some point, let's say X, Y. We drew that table in the previous class. You can just refer the table as to what is the value of this 2P. But the bit at this position, as I scan from left to right, right? So this bit is actually 1 as we scan from left to right, okay? And this initializer corresponds to this 1 bit. The next bit is also actually 1. Okay, so what we do, we check this bit at this position, which is this S minus 1 as per the for loop. And this is the Sth bit. And we go down until we reach the 0th bit. 0th bit corresponds to the LSB bit. Okay, so the if condition is true, which means the bit at this position is 1. So that will require me to do this group operation one more time. So this becomes 3P. Okay, now you can see the bit pattern that we have seen so far and compare it with the scalar that we are generating here. Okay, so this is 1, 1. So the scalar that we are generating is also 3 times P. And if you look at the semantic of the operation that we have done so far, right, that has executed, the multiplication, the group operation on the point that many times, right? So P dot P dot P. 3 times we have executed the group operation on this P. So that's why we have 3P here. Okay. So now moving on, if you go to this particular bit 0, right? This is the second iteration. So the second iteration, whatever is accumulated in D so far. So this is what is there in D. Okay, so whatever is there in D so far, we just take that value and we apply this group operation. Okay, so that will give you 6 times P, right? Because this is 3P, this is 3P. So this is 6 times P. Right? And if you look at the bit pattern accumulated so far here, it's 110. As the bit here is 0, we won't, execute one more group operation with 5, 1 because the bit here is 0. And that is, inconsistent with the bit pattern that's seen so far here. Fine. Now it's time for the last iteration, which is the iteration number 3, where again we go and execute this group operation, D times D. So D has 6P. So if we say 6P, group operation 6P, you get 12P. Fine. And then we go and check the bit position here at the last LSB position. That seems to be 1. So I execute the operation D with P. Okay, because that's the value here is 1. So D is 12P. So this is 12P. Group operation P. You get 13P. Okay, now you can look at the efficiency of this algorithm. See, if normally you want me to compute this 13P, what I'll do is I'll start with P and I will execute the group operation on 13 copies of this P. Right? So I'll first find P dot P, then P dot P dot P, then P dot P dot P dot P. Like that I'll have to go. Right? I'll have to execute the group operation 12 times involving 13 Ps. Right? So that's computationally very expensive. Now, by doing what we are doing here, right, we are reducing the number of computations which are required. If you look at how many times the group operation has been applied here, it's like 1, 2, 3, 4, 5. Right? Instead of applying it 12 times, I have applied the group operation only 5 times. Right? So that's the cost savings that we apply. And most of the ECC implementations, they use this algorithm, which we call as this multiply and add algorithm. Okay, so this is called multiply and add. Or some papers also call it as double and add. Okay, I think so far so good, right? Any doubts so far? Let me just pause here for a minute and then see if you have some questions. Is this fine? So we have just formulated the CCC as a discrete logarithm problem, and then we have seen what is called as this double and add algorithm that will help us to efficiently do that ECC computation instead of just executing the group operator that many times. So can I go on? Is this okay? Okay, so only one response. Fine. So I assume that you are all following me, and I'll move on to this next formulation, which is how to pose this ECC and how to formulate it as a Diffie-Hellman kind of key exchange formulation. Okay. So let us call it as this elliptic curve Diffie-Hellman key exchange. So this is the sequence of steps that we do. Let's assume that there is Alice here and there is Bob here. They wish to exchange some sort of a key or secret between them, right? So the idea is that they wish to derive some sort of a session key or a secret key between them. So the sequence of steps that Alice executes, right? She first chooses a private key. Let's say KPRA is the private key of Alice. He just chooses it by sampling from this particular space, right? So let's say O is the order of the elliptic curve, right? So he starts from 2, 3, and so on, and she goes up to this O minus 1. Right? So she picks one of this key from the sample space from 2, 3 to O minus 1. Okay, and after sampling a private key, what Alice does, right? She computes this quantity, let's say KPRA multiplied by this generator of the group. Let's say P is the generator of the group. So this is the computation that she does. And let's say the quantity that she gets is, say, X coordinate of Alice, comma Y coordinate of Alice. This is the thing that gets generated out of these two computation steps. Okay, and let's call it as A. So what Alice does is, after getting this A, she transmits this A to Bob. Now Bob repeats the same steps, right? So he first computes, samples his private key, let's say KPRB, from the same space, 2, 3, so on up to O minus 1. And then he takes this generator of the group P and he multiplies this integer that he sampled from the space with the generator, and let's call it as XB, YB. Let's call this point as capital B. And Bob transmits this capital B to Alice. Now Alice has both A and B, and Bob also has both A and B. Okay. Now after receiving this B, what Alice does, right? She computes this quantity, which is this KPRA times B. And let's call this quantity as XS, YS. It will generate some point on the elliptic curve. Right? Similarly, what Bob does, he receives this A from Alice and he computes this quantity, which is, this KPRB, that is his private key, multiplied by this A, the XA, YA that he receives from Alice. And I'm going to argue that this will also be XS, YS. Fine. So now they have got the same, the same computation here, right? So without revealing the value of what is XS, YS, both of them are able to compute the same thing, right? It's easy for us to see. Let's say, what is this KPRAB? KPRA times B. This is equal to KPRA. And if you look at what is this B, right? B is nothing but this KPRB times P. So KPRB times P, the generator. So this is, what is this KPR times B? So this is number one. Now if you similarly compute what is this KPRBA, KPRB times A is KPRB times, if you look at what is this A, right, it's KPRA times P. You can see it from here, KPRA times P. So this is KPRA times P. And we know that this group operation is kind of associative, right? So if you do it either way, if you view it as a scalar multiplication, then also you can see that they are equivalent. Or if you just view it as some sort of a group operation, right, then also you can see that one is equivalent to P. Right? So this says that if you apply the group operation KPRB times on P, followed by application of group operation KPRA times, that will be the same as this. Okay, so as 1 is equal to 2, we are able to see that the sort of session key or the secret key that they have established between each other is one and the same. Fine. Now, if you look at this XSYS, right, let's say if I want to use this XSYS as some sort of a key for subsequent asymmetric key cryptographic algorithms. Let's say, for example, I have AES and I want to use this key as a key for this AES algorithm. Now, remember, we should not use both XS and YS because they are highly correlated. If you look at the equation of the elliptic curve and if you substitute the value of XS here, you are going to get this YS. Okay, so maybe YS squared, right? It's what you are going to get. So it's highly correlated. You cannot use the bits in both XS and YS as part of the key. So the usual thing that people do is they just take the XS component of this and then they crop off some bits from this excess, and the remaining bits that are there in the excess is used as the key for this AES. Fine. Now, if you look at it from an attacker's perspective, right, he has to solve a very complicated discrete logarithm problem if he wants to break this particular scheme, right? So, all he knows if he taps into the communication channel are only what is being transmitted, which are this A and B. Fine. As long as the attacker does not know what is this KPRA and KPRB, anyhow, that is not publicly transmitted through the channel. All he has is just this A or B. And just with A or B, right, he will be forced to solve this complicated discrete logarithm problem, which is not easy to crack. Fine. Especially when the order of this elliptic curve, right, it's quite huge. It's a very complicated problem to solve. Okay. So let me take an example so that you can understand this Diffie-Hellman, elliptic curve Diffie-Hellman in little bit more details. Let's take this elliptic curve, which is this y squared is congruent to x squared plus 2x, x cubed plus 2x plus 2. Mod 17. Fine. And let's say the generator of this group is 5, 1. Fine. And let's demonstrate this, right? So let's say you have Alice here. And let's say the private key that Alice samples, the space from which she has to sample the private key is from 2, 3 to 18, if you assume that 19 is the order of this group. Now let's say she samples 3. Fine. Now, how do we compute this value? KPRA times 5, 1. Right? So this is 3, 5, 1. And you can apply this double and add algorithm for computing this. Right? So 3 times 5, 1. And from my table, I'm lifting this value as 10, 6. This is the table that we have already written in the previous class. So this is 10, 6. And this 10, 6 is being transmitted to Bob. Right, so 10, 6, Alice sends this to Bob. Now, after receiving this 10, 6, what Bob does is he first selects this private key, and let's assume that the private key that he selects is 10. Fine. Then he computes this private key times the generator of the group. Right. So this is 10 times 5, 1. And again, if you refer the table that we discussed in the previous class, this is 7, 11. Right. Now Bob transmits this 7, 11 to Alice. Now Alice has 7, 11 and Bob has this 10, 6, which is sent. Right. So now what Alice does is she receives this 7, 11 and she multiplies this 7, 11 with this 3. Right. So this, if you do the computation, it will give you 13, 10 through the double and add algorithm. Okay. And similarly, upon receiving this 10, 6, right, from Alice, what Bob does is he takes this 10, 6, multiplies that with 10. So 10 times 10, 6, you will also find that to be 13, 10. Right? Now the secret that is shared between them is this 13. So the key exchanged here is 13. Now, if you look at the security implications of this, right, it's quite interesting to look at. What sort of attacks are possible on this? So, if you look at it, right, the attacker knows these. Let's assume that the attacker knows the parameters of the elliptic curve, which includes the value of the P, the modulus, and let's say the generator of the elliptic curve, capital P, and he also knows the other parameters, right? So let's say this small a, small b, all of these are the parameters of the elliptic curve. And along with this, if he taps into the communication channel, he also has the values of A and B. Right? A is this elliptic curve point that goes from Alice to Bob, and B is this elliptic curve point that goes from Bob to Alice. Okay, so the attacker has these sort of information. Now, if he wishes to figure out, right, what is the private key of Alice and what is the private key of Bob. So for him to figure out the private key of Alice, let's say KPR A is the private key of Alice, he has to solve this discrete logarithmic problem, right? Which is how many times he has to he has to reach A from P. Right? A is the one that is being transmitted and P is the generator. So how many times he has to execute this group operation? See, this log A base P does not mean the traditional semantic of this logarithm, right? So it means the elliptic curve theoretic formulation, right? So this means how many times I have to apply this group operation on P for me to get A. So this is figuring out this value is KPRA. That's what we call as the discrete logarithm problem. Similarly, if the attacker wants to get hold of the private key of B, what he needs to do is again to solve a discrete logarithm problem that takes him from P to B. Okay, so this is how many times he must apply the group operation on this P to get back B. As we see, both of these are quite complicated, right? So this is just a hard problem to solve, especially for good elliptic curves, right? So which satisfies certain properties. So it's very hard for you to solve, right? There are certain, index calculus based algorithms, right? Which are generally considered as powerful algorithms for attacking discrete logarithm kind of systems. But if you look at elliptic curves, they are not really amenable to index calculation kind of attacks, right? Index calculus kind of attacks. However, some generic algorithms, right, like Shank's algorithm and Pollard's row method, they are all applicable against this elliptic curve Diffie-Hellman kind of formulation. But the order of computations that are required, right, that's simply too high. So for instance, if you take an elliptic curve whose order is n, it requires at least, right, root n computations for the attacker to break the Diffie-Hellman formulation. Okay, I mean the elliptic curve Diffie-Hellman formulation. So if you want to achieve security level, right, of let's say a 2 power 160, right, kind of steps or computations, then you need to use double that, right, like 2 power 320 is the group order that you are looking for, which means you should select a prime which is around this group order, right? So a prime P must be selected, which is approximately of the magnitude 2 power 320. If you expect the attacker to perform 2 power 160 computations before he can crack this Diffie-Hellman scheme, then the form of the elliptic curve that you choose should have a prime modulus, which is of this form, 2 power 320. Okay. Now, when it comes to implementing such elliptic curve formulations, right, what normally is prescribed is to have layers of implementations, because there are several heavyweight algorithms that must be coded, right, and there is a certain way of layering that needs to happen. So, for instance, I'll create a software with these many layers, right? Maybe in the bottommost layer, I'll try to execute some fundamental operations on some prime field, right? So the operations should be addition, then subtraction, multiplication, and inverse finding. So this is done on the prime field. Fine. On top of this operation, right, we can look at the next layer where we code this double and add algorithm. So here in this layer, we have this double and add algorithm. That is implemented. On top of this double and add algorithm, right, what you can have is you can actually implement this, like elliptic curve Diffie-Hellman kind of algorithm or elliptic curve digital signature algorithm. Okay, so this layer kind of invokes this layer and this layer invokes this layer. And if you look at some of the criticisms against this elliptic curve cryptography, right? People usually say that it's very computation intensive. So some of these layers can also be implemented in hardware, right? So let's say you can have some sort of hardware where the hardware is running these algorithms, right? You don't run these algorithms in software for want of performance and for want of efficiency. And again, it's generally not a good idea to play with this because it has a lot of mathematical underpinnings when it comes to countering vulnerabilities. So normally blockchain implementers, right, what they do, they just consult the NIST standards. NIST is National Institute of Standards and Technology, and whichever resilient elliptic curve equations are being recommended by NIST, right? They just take one of those elliptic curve recommendations from NIST and they try to implement those recommendations while coding the CCDH or ECDSA. So maybe with this, I have completed my discussion on ECDH. Before moving on to the CCDSA, let me see if you have some questions. Are you following me so far? Is it fine? Do you have any doubts? Okay, so at this juncture, let me pause for a little bit and pose a very simple question to you. Let me see what are the answers that are coming through. Let's say I wish to do this computation, right? Let's say I wish to perform 26, right, times 5,1. The question is, how many group operations must be performed by the double and add algorithm before I can compute this result? Can I know your answers through the chat window? I'll give you a minute time. Well, I'm getting 3 answers. See, this is simple, right? Like you look at the binary representation of this 26. It is 11010, right? So that's the binary representation. And we scan from left to right and we ignore this one, right? Initially, this corresponds to the initialization of this result with the generator. And then whenever you have a 1, right, it involves 2 group operations. And whenever you have a 0, it involves only 1 group operation. That's the idea. So this involves 2 group operations, this involves 1, this involves 2, and this involves 1. Okay, so which means totally you will execute 6 group operations. And of course, 6 is the right answer, right? So, fine. So with this out of our way, we'll now look at the elliptic curve, like digital signature algorithm. That's the one that's used for signing transactions in your Bitcoin-based blockchains, right? And let's see how it functions. It's quite easy to follow and quite easy to understand. This is the first phase of any digital signature kind of thing, right? It's generating your key. And then the second phase is signing the message. And the third phase is verification of the sign. Now let's see how this key is generated. Of course, we already know that, but let's see it in the context of ECDSA. So we are given with this elliptic curve, and some portion of this elliptic curve will be the public key, right, of the person. Let's say we are talking about Alice. So let's say KPUA is the public key of Alice, and that comprises of some components, right? So one is the modulus, small p of the elliptic curve, then the coefficients which are there in the elliptic curve, and the order of the elliptic curve, which we call as O, and maybe some 2 points on the elliptic curve that we select, right? One is the point A, the other one is the destination point B. Fine. So this all are part of this public key of Alice. When it comes to the private key of Alice, right, there is only one value here, which is this value I, which is the number of times the group operation must be executed on this elliptic curve to take Alice from this A to B. That's the only thing that's private, right? Everything else is public. And so this is how we generate the key. Given the parameters of the elliptic curve, and given the source point on the elliptic curve A and the destination point on the curve B, we just keep all of these parameters as public, and only the number of hops I need to jump on the elliptic curve to get from A to B as the private entity. Okay. Now with this kind of setting, similarly Bob will also have his own KPUB and KPRB. Okay. But anyhow, we will not bother about Bob now because Alice is the one who is going to sign. So only KPUA and KPRA are of interest to us. Okay. Bob is just going to verify using the public key of Alice. Now let's see how the second phase proceeds, which is the signature generation. So in signature generation phase, right, the first step is choosing an ephemeral key, sample an ephemeral key. Let's call this key as K, let's say EA, right? This is the ephemeral key chosen by Alice. So KEA, and this is sampled from the open interval 0, O, right? Where O is the order of the elliptic curve group. That's the first step. In the second step, right, we compute some intermediate point, let's say R, which is equal to this ephemeral key multiplied by the source point A. Okay. In the next step, we just look at the x coordinate of this R, right? So maybe using that, let's compute the signature. S is the signature, which is given by the hash of, let's say, the message. Let M be the message, plus I is the private key multiplied by the x coordinate of this point here. Let me call it as XR. Okay, multiplied by the inverse of the ephemeral key sampled. So KEA inverse mod, let's say, okay, the order of the group, which is O. Right, so this is the signature generation step. I'll tell you how to make sense out of this in a minute. Now in the signature verification step, right, what we do, so in step 1, upon receiving the signature and the message from Alice, these are all the steps that Bob executes, right? So he first computes this quantity by inverting the signature and taking mod of that. Then some auxiliary quantities he computes, which is W multiplied by the hash of the message mod O. And the second auxiliary quantity, which is W multiplied by the x coordinate of this R value that is generated here, mod O. Okay, and D, which is the point that we get, let's call it as P, by executing this computation. A1 multiplied by A plus A2 multiplied by B. Okay, maybe this plus refers to the group operation dot, actually. This is the group operation. Okay, and in the final step, what we do, we take this P and the x value of this P in specific. So let's say if the x value of this P, it's equal to the x value of this R, okay, under this mod P, mod O arithmetic, then we deem the signature to be valid. Okay, and if this x value of this P is not equal to this x value of R under mod O arithmetic, then this is the invalid signature. Okay, these are the steps that we do for verifying the signature. Okay, now let us first understand how this works, right? Why this works actually. A very simple abstract algebraic proof can be provided for this. Let me do that before taking an example. See, the signature is computed like this, right? So S is congruent to the hash of the message, let's say plus the private key multiplied by the x value of this point R that is generated times the inverse of the ephemeral key, right, that Alice has chosen, mod O. So this is the way the signature is generated. Now if you look at the signature and slightly rearrange this, right, what can you get? This ephemeral key is equivalent to, if you bring this S inverse here, this becomes S inverse HM plus I times S inverse XR mod O. Right, I'm just slightly rearranging S and KEA and I'm rewriting this equation. Fine. Now, if you look at the right hand side of this, right, like what we have here, this is equivalent to writing KEA is equal to the auxiliary value 1 plus the private key I multiplied by A2 mod O. Fine. So you can compare this. How we generate this auxiliary value A1, that tells you a hint. See, W is S inverse and A1 is computed as S inverse HM mod O. That's what you have here, S inverse HM mod O. Similarly, if you look at the auxiliary value 2, you have S inverse XR mod O, right? So this is S inverse XR, there's an extra I here, that's why we write it as I times A2 mod O, right? I'm just expressing the ephemeral keys expression in terms of the auxiliary values which are computed at the receiver's end, the Bob's end, while verifying the digital signature of Alice. Now let's see how to establish this equivalence further. Now we know that this A is a generator of the elliptic curve. As J is a generator of this elliptic curve and the order of this curve is O, fine. What I can do here is I can multiply this equation KEA with A. Okay, this is equal to, let's say, A1 plus I times A2 multiplied by A. Now we know that this group operation is associative, and as per the assumption that the group operation is associative, right? And we also know that, yeah, maybe first let me apply this group operation being associative. So this can be written to be A1 times A plus I times A2A. And okay, the way we compute this KEA times A, right? This is yeah, this is A1 times A plus, if you look at this I times A2 times A, this is I times A is how this B is computed, right? So this is because you start from A and you skip on the curve I times, which means apply the group operation on the curve I times, you come to B. Fine. So this I times A is actually B. So I can rewrite this as A2 times B. So this is what is the expression for KEA that I'm getting. And now you can see, right, how I'm entitled to compare the signature while verifying, right? So because I've established the equivalence of A1A plus A2B and KEA times A. Okay, so if the correct signature and key are used, right, this is exactly the condition that we check for in the verification process. Right? So if you look at the verification process, this is what I check. I take the x coordinate of this P, which is just this A1A group operation A2B, and I take this x coordinate and check it with the x coordinate of R. Okay, and R is nothing but KEA. I have established the equivalence of this KEA with A1A group operation A2B. That's what I have done. As long as these two are equivalent, right, I'm entitled to check the signature this way. These are equal, so their x coordinates must also be the same. This is a point x1, y1. This is another point x2, y2. It's enough if I check the x coordinates of these two to verify the signature. This is a very simple group theoretic kind of formulation that we have done to prove that the ECDSA algorithm actually does what it intends to do. Okay. Now let's take an example so that you can understand what I'm doing here. So this is, let's say, a representative example. Let's look at the Alice side of things, right? So first what Alice does is the generator point is chosen. Let's say this is 5,1. And let's say that the order of the group is 19. The same elliptic curve equation that we have been looking at, let's say that Alice uses that elliptic curve equation. And let's take the private key to be 7. Okay. Now what Alice does, she computes this B, which is, let's say, this I times this generator A. Okay, so this I times this generator A, which is, let's say, 7 times this 5,1. And from my table here, the value for this is 0,6. Right, so this is 0,6. This is what I have. Now what Alice does, she let's say shares this, right, to Bob, and these are the parameters which are exactly getting shared, right? So the modulus value of the elliptic curve, the values of the coefficients on the elliptic curve, which are 2,2, the order of the elliptic curve group that's generated, which is 19, and the A value that is used, which is 5,1, and the B value that is used, which is 0,6. Right? All of these are shared from Alice to Bob, because for Bob to execute the verification algorithm, he should know all of this. Right? Now, once this is transmitted to Bob, Alice gets on with the signing process. Right? So how signing happens here? First, he takes this message M and Alice must compute the hash of this message, right? So let's say the hash of the message gives 26 as the value. Next, an ephemeral key must be sampled from 2 till the order of the group minus 1. And let's say the sampled ephemeral key is 10. Randomly, it should be sampled from the from the domain that we looked at. Now, we compute the value of R, which is this ephemeral key multiplied by the source point, right, which is 5, 1. Okay, and again from my table here, the value that it's worked out to be is 7, 11. Okay, so this is 10 times 5, 1. This is 7, 11. Now let's take the x value, x coordinate of this point, and let's compute the signature. We have all the ingredients required for computing the signature. H of m is 26 plus this is 7 multiplied by this is 7, and the inverse of this, right, this is 2, right? So this works out to be 17 mod 19. You can actually work it out and check. See, all I have done is I have just substituted all of these values in this signature computation formulation. We know h of m, we know the private key I, Alice knows the private key I, the x coordinate of R is known, the inverse of the ephemeral key is also known with respect to the group order, right? So this is not the elliptic curve sort, the elliptic curve's modulus. It's not P, it's the order of the group that's generated by the elliptic curve. So, yeah, so this gives you 17 under mod 19. Okay, so it's not mod 17, it's now mod 19. Now, after doing this, right, what Alice does, Alice actually transmits this value of the x coordinate of this R and the signature that is generated to Bob. Right? So the x coordinate of this is 7 and the signature that is generated is 17. Right? Both of this is transmitted through the channel to Bob. Now Bob receives this 7 and 17 and he proceeds with the verification process. Right? So let's see what is this verification process. Okay. So initially this inverse of the signature must be computed. Signature is 17. So its inverse must be computed with respect to mod 19. Okay. So if you compute the inverse with respect to mod 19, I have computed this to be 9. Okay. So this is 9 mod 19. Right, now let's compute the two auxiliary values, which are A1 and A2. And A1 is 9 times the hash is 26 mod 19. Right, so that works out to be, I think, yeah, 6 mod 19. I already have it here. And similarly, A2 is 9 multiplied by this x component of this value that's passed here, 9 multiplied by 7 mod 19. That works out to be 6 mod 19. Both A1 and A2 works out to be 6 mod 19. And let's compute this point P, which is the 6 multiplied by the generator A, which is 5, 1, and this 6 multiplied by this is 0, 6. Okay, so this is 0, 6. And remember, this B point was shared with Bob by Alice in the first step itself. So Bob knows both 5, 1 and 0, 6. Now, if you work it out right, you get 7, 11 as the answer. Fine. Now, if you look at this 7 that we have received here, and look at this 7 that was transmitted from Alice to Bob, right? This 7. Both are matched, and we find that both are one and the same. Okay, so now Bob concludes that the signature is valid. Right, it's quite easy for you to check this, right? Like only that we need to do more number of computations here, right? In the for computing the auxiliary values, the inverses, and so on. Once that is done right, it's really easy for you to kind of check how this works. So this is about this elliptic curve digital signature kind of algorithm, and this is the one that's used in the Bitcoin kind of blockchains, right, for signing some transactions. So having said this, again, let me stop for a bit and then see if there are any questions or doubts. Do you have any queries or questions for me? Right. So if there are no other questions, right, let me just pass on the two links that the professor shared with us today morning, which contains a step-by-step set of instructions as to how, to create a smart contract using Solidity and ask you to work it out, right? So these are the links that I have pinged through the chat window. Please refer to the first link that has a set of step-by-step instructions as to how you can create a smart contract, and just follow the tutorial and let me know if you have some doubts or queries. Fine. So at this juncture, I think I've exceeded my time already. So let me stop here, and uh, I think the TAs will reach out to you for the conduction of mock examination shortly. So I advise all of you, please attend the mock examination through the Code Tantra portal without fail, so that tomorrow we'll be ready to face the logistics of the real examination. Okay. So if there are any doubts, you can ping me through the chat window. Yeah, I am getting some question about the pattern of questions, right? The questions will be MCQ. The questions will be of MCQ format, and you will be given an hour. There will be 30 MCQ questions that you will be expected to solve. Yep, and also I'll be sending out some mail later today for you to set up, right, the truffle Ethereum framework, right, and maybe that is also a step-by-step set of instructions that will help you to set up this truffle Ethereum, and maybe if you can follow the steps that's given there, and let us know if you have some queries so that we can address them. So if there are no such queries, I think thank you for joining me on the penultimate day of this GIAN course on blockchains. And I'll see you all tomorrow morning at 10:30.
Thank you, sir.